It's essentially the small rectangle that's nearby.
Yeah, no, I see it. I'm going back to sharing the screen, yeah.
Okay, very good.
And now I go back to this. And
okay.
And I haven't yet shared the screen with the talk. Let me see if that works by going to full screen. Hold on.
Yeah.
And let me go to full screen here. Hold on.
Exactly like
slideshow. Hold on. Let me play from start. Is that now the full?
Yeah. That works.
Okay, excellent. Thank you.
Excellent.
Fun. All right.
Okay, so we can start.
You can start. Yeah.
So no, wait, just a moment, just for some salutations, and then probably Daniele, you can start with addressing with the salutation by director, please.
So we start a minute in advance. Okay.
Yeah.
This is very nice. Okay. I'm very pleased to bring to all of you the warmest welcome from our rector, the rector of the University of Naples, which hosts this school. And I'm very pleased about that. And I have a couple of slides just to represent what I want to say, because sometimes slides are more efficient to describe something instead of words. And I assume you are seeing the slides on my computer. Okay.
Yes, we can see that.
Okay. So we are very pleased for this school, because this school matches very well our ideas, the idea of the University of Naples, the director of the University of Naples, about PhD schools. The idea is difficult to be expressed in words. It was expressed by Raffaello with this painting. So a PhD school is an environment like this. Please, you can understand all I want to express just looking at this painting. And this course is very appropriate to match with this painting, because there are numbers, there are features that comply very well with the paintings. For instance, the relevance of the research theme. The research theme is very intriguing. It's not to me to say how much intriguing it is, but it is an effect, because you can see how many researchers are working on that. The relevance of this PhD course, because as much as I know, this is the first time that a PhD school is organized instead of a general conference. The quality of a lecturing team, CVs say all, so you can look at the CVs of the lecturers and you can understand how important this school is. Also the importance of the supporting institutions. We have a supporting institution in this activity. The activity is fully funded by University of Naples, but is supported by aggregation of researchers. They recognize this is a key element in this period. And even the audience dimension. We have 250 attendees in this school, which means that the school is absolutely important, coming from 5 different continents. So the audience variety. There are students, there are also professors that attend this school. All these norms testify that the PhD school we are trying to conceive, we are trying to start now, is just in line with the idea of Raphael. And maybe also in the future perspective. Now we need this kind of event for sharing ideas and connect researchers, especially in this period in which connecting researchers means connecting virtually. We cannot connect in person, at least for the time being. So we deserve this kind of events, and we thank Innocenzo for conceiving this kind of event, Salvatore for hosting in the Scuola Superiore Meridionale this kind of events, and so on and so forth. So we deserve, as a research community, this kind of events. We also deserve this kind of event because we want to present ourselves, we, the scientific community, to the entire society. We need to present a unique way, a unique fashion, the scientific community that works all together all over the world in a common project to solve problems for the community. This is most important, since they look at us as someone that can help the society when problems comes up. There is something missing anyhow, and this is something important because Raffaello put this school in an appropriate environment. And the problem is that now we are going virtually, and Raffaello said that we have to work in a school in the appropriate environment. So instead of saying how much important the school is in this event, how much satisfied we are about this event in this fashion, we want to emphasize that we can change our perspective and conceive the new edition, the next edition, with all of you in presence in Naples. This is something to put us in front of our future, to conceive the future, not look behind us, look beyond the next years. And to do that, the University of Naples can offer places, location, like Raffaello tried to say with his painting, including the school in an appropriate location. So it's up to you to select the one. So use the environment, use the floor to decide which kind of environment you prefer. You have here 4 location in the University of Naples, the main location, institutional buildings, or on the right here, the main location for Scuola Superiore Meridionale, or if you prefer, a location in the seafront, again in a modern. And finally, a contemporary location in the sea, in the area of Naples. So please select the location, just to say that we are trying to involve you also in the organization, the next event. The community must work all together, even when the organization is important. We can bring new ideas working all together. For instance, we can include novelties like the inclusion of verticals. So instead of having a very general talk like now, we can have verticals on science, on engineering, on technology, because all this kind of research calls for these verticals. We can have firms involved in that, not only as exhibitors, but also in the speeches or in the audience. We can have a PhD students presentation in posters or some forms of multimedia projects. Please convey your ideas, starting from the location, because we are so satisfied about this event that we are just looking to the next edition. There is one firm point, the chief organizer. So the chief organizer, even in that case, would be Innocenzo, which is the chief organizer for that. So a very warm welcome to all of you for being here virtually in the University of Naples. The same from the rector of the university, and enjoy this first course of gravitational waves. Thank you to all of you, and very welcome.
Okay, thank you, Daniele, for this nice presentation of all our activities. And first of all, I would like to thank the speaker on the behalf of the whole organizing committee for having kindly accepted the invitation to participate in this workshop, which is very important for our students. I am the scientific coordinator of the PhD in space, which deal with the cosmology, space science, and space technology within the Scuola Normale Superiore, which is a school of high scientific and humanistic training. It is based on the model of Scuola Normale di Pisa and the École Normale in Paris. And we have various excellence areas, for example, the Greek-Roman archaeology, space science, genomics, complex systems, advanced chemistry, applied mathematics, global history, and in particular the history of Mediterranean countries, and so on. So the purpose of this school is to train talented young people and to direct them primarily toward advanced research. And it is important to stress, like Daniele told before, that this school is also equipped with an Institute for Advanced Studies, and then we are pleased to have you after pandemic in a more relaxed situation. So, as Daniele said, this workshop would like to be the first in the space area, and we are honored to start this activity with the personalities that we have collected for it. So I wish you a fruitful listening to our prominent speakers, and I wish this especially to the PhD students. Thank you for your coming.
Hi, Ian. How are you? I am good.
Yes.
Warm but good.
Good.
I think I'll just-
You are in holidays last
Please.
week. Yeah.
Innocenzo, please.
Yes,
It's up to you.
Yes, first of all, I will repeat my warm personal thanks to our highly distinguished lecturers for accepting my invitation and making this school possible. Next, I'd like to thank the SSM for supporting me in organizing the school on occasion of my recent move to my former alma mater after spending most of my academic career elsewhere. My special thanks go to our younger colleagues, Nicole Benetti and Marco Coraggio, who helped a lot in the organization. Introducing our speakers is a difficult task, but it is also an easy task. For those who are already in the field, their very names are enough, because everybody knows their original, fundamental, prominent contributions to the state of this art. Those who are not yet in the field will be most certainly captured by their lectures, and this is precisely one of our aims and goals. When it comes to our first speaker, Professor Rainer Weiss, there is one special word in Italian that fits well, and the word is maestro. In English, a guide, a pioneer, a master. Ray is a man with a vision, a genuine, cultured, strong, and gentle human being, and an outstanding researcher and teacher who had a unique role in making the dream of detecting gravitational waves real and motivated many talented researchers to find their way in science and in life. It's a great privilege for me and for all of us to welcome him here. We received as many as 250 registration requests for attending the school from all over the world, as Daniele already mentioned. In view of the international character of our audience, I will add a few words, forgive me to take a little bit more time, about our university, the University of Naples. Our university was established in 1224, its nickname being the name of its founder, the Roman German Emperor Friedrich II. Throughout the centuries, in the light and the darkness of its long history, Naples gained a status among the capital cities of European culture, on a par with Madrid, Paris, Berlin, St. Petersburg, and Vienna. And its university flourished in all fields of science, medicine, and humanities. In a world with no borders like our own world, keeping up with such traditions is only possible looking beyond one's own courtyard and its rituals in a truly frontierless perspective. This is certainly a challenge, but this cannot be circumvented. The involvement of our university in relativity and gravitational wave science dates back to the early days of GR. Roberto Marcolongo, a professor in this university, taught a course on general relativity and its mathematical foundations in Naples as early as 1919, the same years when Sir Arthur Eddington published his most famous treatise. Marcolongo's lessons were republished recently with a commentary by Professor Merola from the same university, and are still a very interesting reading. Notably, Marcolongo's approach was based on a coordinate-free approach, following essentially the steps of another Italian scholar, Burali Forti. The noteworthy traditions in the study of relativity continued until our days in this university, with the work of Giuseppe Marmo and Ruggero De Ritis, and their many pupils, and is still lively with Giovanni Avellino Camelia, Salvatore Capozziello, Cosimo Stornaiolo, just to mention a few, apologizing in advance with those whose names don't come to my mind right now. In the sister University of Salerno, the group led by Professor Gaetano Scarpetta gave important contribution to the study of gravitational lensing and dark matter. The University of Naples joined and supported the Virgo project since its very beginning, and still harbors an active Virgo group hosting some talented young scientists. The founders of the Virgo Naples group were my good friend and Professor Salvatore Solimeno and Professor Leopoldo Milano. Leopoldo was an acknowledged astronomer and an old-style gentleman. He passed away a few months ago, and I think all of us will join me in dedicating this school to his memory. This is all I wanted to say. My apologies for taking perhaps too much of your time. I wish everyone an enjoyable and fruitful school. One practical detail before starting. Those of you who are connected via the MS Teams platform, please use the Raise Your Hand tool to request a question slot. Questions will be made in the break or at the end of the lecture, as Ray probably will allow us to do. Please introduce yourself before asking your questions. Those listening anonymously via the YouTube channel may also make questions. These will be filtered for nonsense and proposed to the speakers on the basis of their deemed relevance and the time available. Ray, I am sorry. I apologize, especially with you, for taking part of your time. I am sitting and enjoying your lecture as usual.
Well, I hope it's good enough. I mean, after that big introduction you gave me.
I'm sure it is.
Well, somebody has to put my screen back. That's not my job. I can't. Should I go back? Is it my job to put the screen back?
Yes.
Oh, it is. I didn't realize that. Okay. So I have to do that. Okay, here we go. Let's hope it all goes. There we go.
All
How do
right.
Okay, very good.
I have to get rid of that black thing in front of me. What is that? There we go.
Okay,
Good.
perfect.
Okay, we got it.
Please,
Everything is
start.
good? Excellent. Wonderful. Well, first of all, thank you for asking me to give a talk. And first of all, I didn't realize how much of the history of the relativity actually comes from the southern part of Europe. I thought a lot of it came from the guy I know best is Levi Civita, the mathematicians. And but I didn't realize so many physicists were in it. So that's a very important piece of knowledge. Well, let me start because it's kind of a long lecture. And here's the outline of the lecture. And I've tried to make it so I could bring you into this field without a lot of experience, but there will be times when you will be asked to know a lot. And let's see how well that works. Anyway, it's broken into these different regions. First, there'll be a little history, which we'll talk about in a minute, and some of the basic ideas of gravitational waves. And that'll be followed by how interferometric detectors work, and also a little bit about their what's really behind the idea, and then how they evolved to being tools that would be sensitive enough to do the measurements. Then it's followed by something which I'm a little embarrassed by, because one of your speakers in this course is also going to be talking about similar things, and that is the person who's going to talk about thermal and quantum noise. Well, Sergei Vyachnin, and he will do it better than I will. So I advise you to not miss his talk just because I talked about it. Also, I need to, because it drives the detectors. You can't talk about the detectors without the limiting noise, because that's where all the development went on. Then I'll talk very briefly about the detection itself and the beginning of gravitational waves, and leave most of the science to Bernie Schutz and to Cornish, so they have something to talk about. But then I finish the talk with development of the detectors and what is going on in the field in general. I think that might be most important to many of you. So let me begin with simple beginnings. Well, most simple beginning you can think of is to begin with Isaac Newton. Most of you know about Newton through Newton gravitation, and through this very famous relationship, which is the relationship of how you get a gravitational force from two masses that attract each other. And we note that the force between them gets smaller as a square of the distance. And then there's a constant that depends on the units that you use. Now, this is a wonderful equation. It was the beginning of science, really, because here was Newton doing something which was important on the ground, here on the Earth, and also in the heavens, which was unheard of until Newton, really. A theory, a man-made theory that worked both on the ground and in what you could see in the heavens. And that was the unification of science, which was very, very important. It's a wonderful equation. You don't need much more of that to explain almost everything that you and I normally deal with. You can explain the tides. You can explain why you are stuck to the Earth. You can explain why the Earth goes around the sun. It works beautifully. But in some regards, it doesn't work well enough. And in the two regards that are most important to us is when you get to large masses, masses that are very much larger than our sun, and velocities that are closer to the velocity of light, this theory doesn't work at all. It's just wrong. And there is no news function, N-E-W-S, news function, a carrier of gravitational information. There is no such a thing in Newton's theory. And those are two very important pieces that were brought in by Einstein. And here then is Albert himself, much older than when he developed this equation, which is the replacement for the Newton equation. It's a very difficult equation. It's not easy to solve, and you get easily fooled by the solutions. And Einstein often got fooled by his own solutions, as did a lot of other people. In particular, the people trying to figure out if there really was such a thing as gravitational radiation. But what does this equation tell you? The equation says something which I'll try to illustrate to you in a picture. But what it says is that the way space and time evolve, or how you measure space and how time evolves, which is on the left side of this equation, is somehow related to the distribution of matter and energy in the space. In other words, the matter and energy in the space determines what the space looks like. And that is a completely radical idea, completely different than Newton. There are no forces in the theory. It's a completely different way of looking and is elegant in many ways, but also quite difficult to comprehend. So here's a little picture which does a little bit to try to help you understand it. I come from New York. Now, I'm originally from Europe, but in New York, when I was a kid, we played in things called jungle gyms. These are big it's a big tower you make of crossbars, 1 meter size crossbars in the X direction, the Y direction, Z direction. You make yourself a jungle of squares and cubes, and you can crawl around inside that jungle. And that's called a jungle gym in the United States. Well, here is a cut through the jungle gym. And here it is out here, nice and regular. All the bars you put there together, they're nice and square. And now you put the sun into this jungle gym. We're taking a two-dimensional cut through it. And what the sun does is it makes a distortion in the space. That's what the Einstein equations imply. You put matter into the space, and it distorts the space. So it becomes curved. That's one thing it does. Here's the Earth, and it does not as much as the sun, but it does its own little bit of curving of the space as well. What's missing in this picture, mostly because I've been too lazy to put them in, is many, many clocks. This out here, you put clocks at every intersection where you have bars coming together, you put a clock. And all these clocks out here, where everything is nice and flat, they will read the same time at the same moment of time. So the same time at the same moment in time. And as you look at the clocks that are placed in here, you'll find that they're not going as quickly. They're going more slowly. They're in this curved part of space, and that says that time is also affected by the matter that you put into the space. So you get distortions of space and really distortions in time as seen. And that then is the new thing. And what happens is that the Earth and the Sun make a distortion in the space and a distortion in the time. And that distortion tells them how to move. That's the way Einstein conceived of gravity. Now, in this theory are gravitational waves. And now let me take you immediately to that. And now we begin to talk about gravitational waves. They're required by all theories of gravity that involve relativistic motion. But let's not make too much of a fuss about other theories of gravity. Most of them are not worth it to even talk about. The Einstein theory has been proved to be right so many times and so often, and is so accurate to as much as we know. It's the best theory of gravity we have. And there are sources of gravitational radiation. They are accelerated masses. Masses that accelerate make gravitational waves. Very much like in electricity and magnetism, accelerated charges make electromagnetic waves. These waves propagate at a velocity that's assumed to be the velocity of light. That was one of Einstein's gut instincts. His stomach told him it had to be the velocity of light. There's no other way it could have been, but he didn't know that. He guessed at it. And there were some good reasons to guess at it. And now, as you will find out in this talk, we know for a fact that velocity of propagation of gravitational waves and the propagation of electromagnetic waves are the same to an enormous precision. Now, this is fancier talk, but in the lowest order of gravitational radiation is quadrupole radiation. Why is that? You can have that also in electricity and magnetism when you have radiation from equal charges, plus charge and a plus charge. And that will, as they accelerate, they will still radiate, but very, very poorly. But in gravity, there is only one sign of mass. There's only one sign. That's all we know about. And therefore, the only kind of radiation that exists of gravitational size is going to be quadrupole radiation. And in the weak fields, which we'll get to in a minute, the kinds of things that we measure at the Earth, the equation that you have learned for the propagation of any kind of wave also works for gravitational waves. In other words, the spatial derivatives of the gravitational wave, which has this is the symbol for the gravitational wave, h, and that has both time dependence and spatial dependence, and to make a wave equation. We'll get to show pictures of that in a minute. So the first thing is I want to show you how you can use a gravitational wave. And this is a little bit subtle, and you don't have to understand everything I'm doing here, but some of you will understand it, and it will help you. In other words, in the general theory of relativity, which we'll get to, I won't get to any more deeply than you will get some of that from Damour, who is giving one of the lectures in this series. There's something called the interval. This is the distance between two objects that are separated by two coordinates. And then there is a thing that tells you how you take the coordinates and convert them into something real. Something real is a separation, and that'll be in 4 dimensions. That'll be time as well as distance. But that thing right there is called the metric tensor, and is a thing that converts distances, that's your coordinate distances, into real distances. And that metric tensor is normally made in two parts. One, which is the kind that everybody deals with all the time, is called the Minkowski Metric, which is what we live in. There's nothing funny about the space in X, Y, or X1, X2, X3, or X, Y, and Z. And then here's time. And what is added to the Minkowski Metric is this new little thing, which is the gravitational wave. And we'll understand what that gravitational wave does in a minute, but you add that to the metric already that is there from us living in the world. That's the Minkowski metric. But it's very, very tiny. The Minkowski metric is all of order unity, and everything else is zeros. But all these h's are very small. You'll see they're so small, in fact, they're almost impossible to detect. And so consequently, we can put them into this thing and add them with impunity. And there are two ways of making gravitational waves. Just like in electricity and magnetism, there is, and this is the wave traveling in the x1 direction. It has no components. It's a transverse wave. The wave does all the things it does, perpendicular to the direction in which it's moving. And one kind of wave has this diagonal term, H22 and H33, or it has cross terms, which are H32 and H23. These are two polarizations of the wave, and they look like this. In other words, the wave is traveling with the velocity of light and in the one direction, and and it either exerts whatever it's going to do, and we'll show pictures of how that exertion takes place. It compresses space in one dimension and expands it in the other, as you'll see in a very pretty picture in a minute. But you can have the two waves, and they have different polarizations. They don't interact with each other. Something which has this polarization does not interact with it. You can add them as individual members of the wave, just like in electricity and magnetism. You can add a parallel, you can act an E polarization in the X direction and a Y polarization in the Y direction, add them to the wave propagating in the Z direction. And when you measure gravitational waves, you have to measure both of these polarizations to understand what's going on. Now, I want to show you this because this is the heart of the whole idea. It shows you how you actually measure a gravitational wave by sending signals from one object to another. So what is in this picture is a gravitational wave that's moving in the one direction, that direction here. There it is, moving along. And what you do is you put an object in here, let's say at point x2, and another object at x2 plus delta x2. So you have these two objects, and you have two clocks. And the gravitational wave is traveling between them. And here's the experiment you're doing in your head, a Gedanken experiment. You're sending light from this mass to that mass and then back again. In other words, that's a simple experiment you're doing, and that is extremely easy to calculate. You can almost do this calculation without knowing much general relativity. Because what you know, when light travels from one place to another and comes back again, that's an interval. That's how long you've gone, how much time has it taken for the light to travel from here to there and back again. And that, combined with the spatial parts, gives you a 0 for the interval. And so here is that interval expressed as in terms of in terms of the coordinates. So it goes as a square of the velocity of light times the time interval for the light to go back and forth. And now here is where you put the Minkowski metric, and you add to that the gravitational wave metric. And you multiply that by this separation between the two masses. This is the equation, the fundamental equation of the detection. You'll see. Because now if you let the time be very small, and that means that the wave frequency, for example, is high, or the wave vector is small, then you can, and h itself, the value of h is very small. You can just separate these out. You can make this whole expression, take the square root of everything. You get a 2 here. You take the square root of that, and that gives you 1 plus h over 2 times delta x2 is equal to c times delta t. Now what you do is you divide this through by delta x2, and this ratio, this is the inferred strain in the wave. In other words, this is how much the wave changed the time or the distance, and this is just the separation between them. This is the quantity. This is the inferred distance that the wave has gone between the points. But it isn't any exactly delta x2 anymore. It's got in it now this new term, which is the gravitational wave itself. And so a change in distance between these two masses divided by their separation, and the change in distance comes because the gravitational wave goes between them. That then is equal to h, which is the quantity which is like the electric field in the gravitational wave divided by 2. I will show you a nice little picture of that in an instant. And let me do that right away and then come back to that slide. So here is the picture I'm talking about. This is you in a picture, and I'll come back to the other slide in a second. This picture is going to move in a minute, but here are you. And this, remember, this is now a gravitational wave coming at you or coming out of the screen. So it's going in, and you are right there with the little red square in it. And these are little dots that have been little masses that have been put into the wave. And here's what this looks like. Here's what a gravitational wave looks like. It's coming at you. You'll see right away what I was talking about. The wave is a transverse wave. And you'll notice, for example, that in the, let's say, x2 direction and x3 direction are the different, the motion is, they're 180 degrees different. It's stretching in, let's say, the x2 direction when it's shrinking in the x3 direction. Then it keeps flipping back and forth. That's a very important ingredient of the gravitational wave to allow you to think about how you might go about detecting it. So that's very important. The other thing is that here are you, and when the objects that are close to you don't move very much. These two, for example, they move a little, but not anywhere near as much as the ones over here and over there. And those are the ones that this then along any one dimension is in fact a picture of a change in length divided by a length being the same all along the line. In other words, it's the same as though you had taken a rubber band, and you and a friend of yours had taken a rubber band, stretched it, made little marks on the rubber band. And as you stretch it, it does exactly what goes on in that picture. The amount of delta L divided by L is the same as you stretch it. So that's the field quantity. And it's positive in one direction and negative in the other. So if that's very important that you understand that picture, because otherwise you won't understand any of how we went about detecting these waves. So, all right, let me now go back to the slide before this, which is a piece of history, which is kind of interesting. In Einstein's 1916 paper, Einstein developed his theory and published it in 1915. But in 1916, he wrote a paper which was about perturbation theory in general. How do you apply, how does the full theory, you don't have to know the whole theory. Why don't you, let's look at simple cases which don't have very strong fields. And is in that paper that he finally develops the idea of a gravitational wave. And he makes a big mistake in that paper, and he corrects it in 1918. And by the way, all the papers, all the Einstein papers are on the net. I think they're at least in English and German. I don't know if they're in Italian, but you can go to the net and look up all the Einstein papers yourself now. And so it turns out in that paper, when he finally gets to it, and he talks about, I will just point to this equation that he's talking about in the very last paragraph. In the last paragraph of that paper, he says, and I'll say it in English, it's underlined in red in German, in any case you can think of this equation, which is a source of gravitational waves, and this is the power in the wave. A is the power in the wave. That's the source of the wave and what the motion are in the solid. It says, in any case one can think of A, that's the power in the wave, will have a practically vanishing value. And in the next sentence, which I didn't copy, he says it will never play a role in physics. And the reason's very simple. And here is the other piece that's very important. And these are useful equations for you if you want to just dabble yourself in trying to figure out how much of a strain, how big of an H you might get from some source you have in your mind. And by the way, as long as we're talking about equations, I'll get back to this equation in a minute. But this is the equivalent, right here is the equivalent of the relation, what's called the Poynting theorem for gravitational waves. This is it right here. It says that the number of the energy per second per centimeter squared in the wave is equal to a terrible constant, which is gigantic, as you can see over here. C cubed divided by 16 pi g in CGS units, but you can make your own units. But the important thing is it's proportional to, just like an E and M, it's proportional to the square of h, but it's the derivative of h, the time derivative of h. So S, the amount of power per area, power per area in the wave, is proportional to the square of the first time derivative of the strain, and with this terrible constant. And so let me show you, this is why Einstein must have come to this conclusion himself, because in 1916, when he probably put numbers on the back of an envelope, he thought maybe you can see the gravitational waves from the collision of a train with a wall, any kind of acceleration that is non-uniform. Well, anyway, let's put some numbers in for ourselves. The train might weigh 10 to the 5 kilograms, and before the train was moving, it was moving with, let's say, 100 kilometers per hour, and the time for the collision to smash up the train like that might be 1/3 of a second. That might be a little too short. With those numbers, you have to go out in the radiation zone, so you have to go at least 1/3 of the distance, 1/3 of a second in the velocity of gravitation of light out, and you find out that the strain generated is 10 to the minus 42. That comes from the equation which I should have described to you, which I will in a minute. But in other words, this very dramatic event, which should have shook up the whole world, if you were near there, everything would have shook around you. You would have never melted a thing. 10 to the minus 42, imagine that. A change in length, for a length, is so small that you would have never noticed it. So and we'll get to another example in a second, but I should have gone to this equation first. This, by the way, using this pointing theorem gets you a very useful equation, which you can memorize. It's so simple. It says h, if you want to calculate the value of h from something that's moving and causing a collision or orbiting or however, what you have to do is get the Newtonian potential, which is gm over r. That's that. Divided by the value of the velocity of light squared. That's gm over rc squared. That turns out to be a dimensionless constant. Okay? And you and I are living in a value of that dimensionless constant of about 10 to the minus 10. 10 to the minus 9, 10 to the minus 10. So on Earth here, we live in a tremendously weak, horribly weak field. Gm over rc squared is such a tiny number. Plays no role in anything except pulling us to the Earth. I mean, and it plays no role in atomic physics as best as we know. And it finally begins to play a really big role when you get on the surface of the sun, for example. It might have, this part might be a part in a million. Or when we get to black holes, this number is about 1 at the event horizon of a black hole. That's serious gravity. Now, to make it into radiation, you have to multiply it by the velocity of the collision squared divided by the velocity of light squared, beta squared. And that is, in fact, what I did to get these numbers for the train. Not to waste a lot more time, I'll just tell you what this is. This is, suppose you decided to look in a telescope and look at a binary system of stars. I mean, Einstein knew about binary systems of stars, and he didn't know about galaxies, but suppose they were orbiting, it took 1 day to orbit. You find out that the h value for that is 10 to the minus 23 with a half-day period. In other words, the thing looks the same each time it goes around 180 degrees. Look, it keeps going on. So it turns out that that is the number you will see later. We are now in the business of trying to measure things like that, but not with periods as long as half a day. That's going to be later in the next decade. But when you look at this through a telescope, and you say, how could you watch this thing get smaller because it's radiating gravitational waves? Namely, could you see these two objects falling toward each other and the gap between them getting smaller? Well, it'll take you something like 10 to the 13 years of motion of that thing before you can see that gap change by 1 over e. So Einstein must have, these are the arguments why Einstein came to the conclusion that this was never going to be of any value to anybody. And that was actually the case for a while. Now, the first person who tried to do something about this was Joe Weber, who was a physicist at the University of Maryland in the United States. And his idea was to look at that stretching of space in a great big aluminum bar. This is a great piece of aluminum, almost as you can see, here's Weber himself. This is bigger than he is. And he was hoping that a gravitational wave will come along, strike this bar, stretch it in this direction, and compress it in, let's say, that direction. And he's putting these little strain gauges on the bar so that he can measure that when it happens. He takes this whole big bar, sticks it in this vacuum system up in here, and puts the cover on it and waits. A very clever idea. And, well, it had an unfortunate end. In 1969, he publishes a paper about him having one of these detectors near his office in Maryland, which is one of the states of the United States, and then at a golf course something like 10 kilometers away, and a third one 1,000 kilometers away at a place in Chicago, which is in the middle of the United States. And he was doing something very good. He was looking at all three of those bars and hoping he could find a coincidence excitation of the three bars, that all three bars would suddenly begin to sing at the same moment. And that he was hoping would be due to the fact that a gravitational wave had come in from somewhere and hit the Earth. Well, he did that for some number of years, and it was well known to a lot of people that he was working on that experiment. And he publishes a paper saying that now, after a half a year of collecting data, he had sort of typically 2 or 3 events a day that were coincident in all those detectors. And the conclusion, the only conclusion he could come to, was that that was certainly gravitational waves. And it even became better, as when he looked carefully, at what time of day did these bars get excited. It looked like they were excited when their long length, the long length of the bar, when that was the perpendicular to the bar's axis, either pointing this way or that way, was pointing toward the galactic center. He had a slight peak, he thought, in that. Well, that got everybody very excited. And by the way, in Italy, there were 3 very big, good groups, 3 at least. And all over Europe, there were at least 3 more. And then in Asia, there were groups. And in the United States, there were about 3 other groups that thought this was not such a horribly hard experiment. And they would do it as well. And here is the misfortune. None of them, nobody, was able to confirm Weber's result. And in physics, that's an important and very good feature of physics, that if an experiment is done, comes up a result, others can do it, and they can see it for themselves. And Weber didn't accept that hypothesis, didn't accept that fact. He kept saying in meetings where he went to, when he listened to other people saying, we don't see what you see, he said, you didn't do it my way. And that's not a way you deal in physics. If you can show you have the sensitivity and you have a better idea, it's not done the same way as the person who first saw it, then all the power to you, all good ideas should be accepted. And he refused to do that. And that cost him his career, as far as I'm concerned. Although he had the idea to do this first, there's no question. Everybody who thinks about this always should think about Weber as the one who broke the ice developed by Einstein. And the reason was simple. The technology was changing at a very rapid clip compared to what it was from 1916. So the way it now is being done, and this is the last simple piece I have, is it's being done by interferometry. And here is this very simple way of looking at interferometry. This will be an animation which you will notice in a minute. But here is a laser. That's a laser. It doesn't look like one, but it's a laser. That will put out a light. It'll go to this beam splitter, which is the device that sends half the light through it and reflects half the light away from it. And that's all glass will do that. Every material that is transparent reflects a little and transmits a little. And that light then will go to a mirror, which is a full mirror, come back again, and go back and gets transmitted to this photodetector, which is right there. The same thing happens to the light that gets transmitted. It goes up here, gets reflected, comes back again, and hits the mirror. And I want to show you what goes on. What's been carefully done, by the way, is that the time it takes the light to go from the beam splitter to that mirror and back again is the same exactly as the time it takes the light to go here and back again. So the light spends equal times in the two arms. That's how it's set up. Then a gravitational wave coming in from above will come in and move these masses, just like pull one in, push one out, and then reverses the direction. It keeps reversing whether it pulls or pushes. Okay, so here we go. Here's the animation. The red light is the light power, and the wiggling thing in the light is the electric field. So here's the light reflecting on both sides, and because the times are the same, no light goes through the photodetector at all. That gets explained later in our talk. And now what happens is now comes down a gravitational wave, stretches one arm and shrinks the other, and when that is unbalanced, you'll notice light goes to the photodetector. That, by the way, is about as simple a way as I can show you how the detectors that we're going to be talking about for the rest of the time actually operate. Okay, so that's it. And now we'll go to some real apparatuses and go on to make it further. And let's except for why I forgot Mr. Thorne. This is Kip Thorne, very good theorist. He happens to be a theorist at Caltech, California Institute of Technology. He's an expert on gravity, and that's his business. And over the years, he has became really wanting to understand how much gravitational radiation might there be coming from objects that are out in the universe. And he and his group did a lot of work on that, as did others, but their group is really well known for it. And they said the following, and Kip in particular, here's H, and this is what H means again, delta L divided by L, the strain. And they came to the conclusion that if you want to ever measure something from the universe, you had to be able to measure a strain that was larger, that was smaller than 10 to the minus 21. That's a very small number, a tiny number. And a way to set it properly, the detector that did make the detection ultimately had an arm length that was 4 kilometers long. And the delta L for 4 kilometers, if you have a strain of 10 to the minus 21, is 4 times 10 to the minus 18 meters. And that sets the scale for the whole field. And there's where the experimental challenge comes. And that's why it took so long. But, and a couple of ways of saying it, and these are the things that we will be talking about, is that if you use light and you say how big is the wavelength of light compared to 10 to the minus 18 meters? 10 to the minus 18 meters is much smaller, 1,000 times smaller than a nucleus of an atom. It's smaller, much smaller than an atom. Smaller even than the nucleus of an atom. So you're talking about somehow learning something using light, that is 10 to the minus 12 times smaller than the wavelength of light. That's a challenge number one. It turned out that challenge isn't so terribly hard. A much harder challenge is if you take those mirrors that I showed you in that animation. You have to somehow isolate them from everything that's moving. And the Earth under you, you're near the Mediterranean, so it's even a little worse. But typically, everywhere in the world, and by the oceans, it's about twice or 3 times as bad. The Earth is moving about 1 micron, 10 to the minus 6 RMS, root mean square motion of the Earth everywhere is about 10 to the minus, few times 10 to the minus 6 meters. So again, you have to beat that motion down to part in 10 to the 12. And that's the thing that took so long. And also all sorts of other forces that get in the way. So here is a little bit about a Michelson Interferometer, which is what you were just looking at. Let me explain what this picture is, and this is what was in that picture that made the animation. If you're looking at the detector, this is the power at the detector, and this is the displacement from 0 is a displacement from equal paths. In other words, the path lengths on those two arms are equal when the path difference is 0. And you'll see certain spots here. There are two ports of an interferometer. One port is the place where you put the laser. That's where the laser was. That's called the symmetric port. The symmetric port. And then there is another port, which is the anti-symmetric port, is where we put the detector. You had all of those features in that animation, but I didn't tell you about them at the time. And now let's look at let's look at what happens at the anti-symmetric port, which is at the detector, if you have exactly 0 path length difference. Well, it's this red line. There's no light at the photodetector at all. You can see it's the red line. But where's all the light going? All the light is going either back to the laser, or it's going back to the laser. That's where it's all going, or someplace. But it's not going to the detector. And so here is you can see the way what's happening is there's a flip of the light. When there's no light at the detector, all the light is at the laser, going toward the laser. Very bad business, and so forth. So this is the kind of thing you get. And what these other curves are mostly, if you have mirrors that are actually perfect. But so the big thing you notice in this picture is at the two ports, when you have no light at the anti-symmetric port, and we'll see in a minute why it's called the anti-symmetric port. All the light goes to the symmetric port. Okay, so now let's start looking at an interferometer. Oh, sorry. Before we do that, one more educational bit. This is maybe an insult to some of you, but it's worth knowing that we all are on the same page here. This is more for what people would call electrical engineering. The hell with that. Turns out everybody has to know this. And this is what you can do with sine waves. We're going to be full of sine waves in the next hour and a half. Oh my God, well, okay, I'm using up a lot of time already, but certainly in the next part of the lecture, we're going to be talking about sine waves all the time. So you have to know two things. So here's a picture of a sine wave that you know. Here's a description of a sine wave as a phasor. In other words, here's call it the electric field or whatever, and it's going around at the frequency omega naught. And if you look at the spectrum of that, there's only one color in that particular waveform. It's a waveform which has one spike at exactly omega naught. That's in our instrument that measures the frequency of the light, or the frequency of the sine wave. So this is the simplest thing you can get. A single sine wave. It has a phasor which keeps going around and around in one direction. If it's omega minus omega, it goes the other way around. And it has a one spectral line in a spectrum analyzer, and it's expressed as an electric field in time, the real part of e to the I omega t. Okay, that's the carrier. You'll hear me call that sometimes the carrier field. Suppose you have amplitude modulation. That's what this looks like. Suppose you have not a perfect sine wave anymore, but you multiply a sine wave with another one and look at the amplitude change. Okay. Well, the way that looks, it looks like that. But audio radio works that way. Or me talking to you works that way. And so what you have now is here's the carrier going around still, but you now add to it two sidebands, which cause the vector to change. In other words, this sideband is going around in such a way that it always adds or subtracts, but along the direction of the carrier. Okay? In other words, as the carrier wiggles, it always goes back and forth along the carrier direction. And that is the same as multiplying it by a sine omega t. And you now get three frequencies. You get the carrier frequency and one band above the frequency of the carrier, separated by the carrier by omega of the modulation, which is the speech or whatever you want to call it, and the other one below it. And the amplitude of this depends on the amplitude of the modulating signal. There's another kind of modulation which looks very different. And that's this one. You can see what's going on. It's modulation that's causing the sine wave not to keep a constant frequency or an expectation that the phase keep changing in a systematic way. You'll notice it keeps wiggling back and forth. And in this case, it's a modulation which doesn't change the length of the carrier, but it changes how quickly it moves in the rotation around. So sometimes it goes backwards, sometimes it goes forward, and this rotates at omega m. Okay, that's the modulation frequency. And what that does, it does something very similar in the spectrum, but it has the two sidebands have opposite sign. And so it turns out we would be encountering this over and over and over again. In fact, when we now talk about how a gravitational wave of a given carrier, how a gravitational wave of a given frequency interacts with light in an interferometer, it is by imposing phase modulation sidebands on it. You will see this as we go along. That's why I want to show you these pictures. And here, as soon as you have more than one member to the spectrum, you have to take count of that. And here you can see it's an e to the I omega naught t, and that's for the carrier. But then the sidebands, they have the frequencies on either side, minus and plus, and gamma, which is called the modulation index. And here it's a plus sign for the two sidebands, and here it's a minus sign for the two sidebands. Okay, so have that in your mind as we go on in this talk. Okay, so the very first thing I want to talk to you about is what happens if you have a mirror that's moving. Suppose this is a mirror oscillating back and forth. And you send a carrier light at the mirror. What happens? Well, that mirror acts like a phase modulator. So it moves away, and you look at the reflection of the reflected light. There's a little more time, a little less time, a little more time, a little less time, so forth. And so what that happens is you get exactly that phase modulation. You get the carrier coming back, and then two sidebands, they have different frequencies, and they come back from this. In other words, the whole technique that we're going to talk about now of how what you saw was the light on the detector going on and off. There was something a little more subtle going on top of that, and this is what's happening. We are actually generating sidebands of the carrier light by the motion of the mirrors, which are induced by the gravitational waves. So here's a picture describing that. And this has in it that model with all the dots, but I want to show you a little now in detail. This is a Michelson Interferometer. What we already talked about in that display in the animation is the laser, the beam splitter, and these are the two far mirrors. And here's the photodetector. It's exactly the same setup, but now we have a lot of symbols in here. And these arrows, which I will help you, are the arrows that show you which way the carrier is a big red vector pointing up, and the area and the purple one shows you the direction in which the light is moving. So the laser, as it leaves the laser, comes to the beam splitter. Now there's a very interesting thing about a beam splitter, which I didn't tell you about. But the beam splitter has a positive sign and a negative side. This is what makes the difference. This side will be the symmetric side. That side will be the anti-symmetric side. And this is due to the coating that you put on the glass to make it reflect. And the Maxwell equations and satisfying the boundary conditions. And what happens is when you reflect the light from the plus side, and you reflect it, here you can see, you reflect it, sending it to that mirror, you have a smaller amplitude of a little bit, square root of 2 smaller amplitude of the electric field because part of it's over here. And it comes to this mirror. That mirror then is jiggling back and forth due to the gravitational wave. It's wiggling back and forth. And the light comes back from that mirror. And now it has two phase modulation sidebands on it. because of the wiggling frequency due to the gravitational wave. And so here they are. Now we have the carrier and one phase modulation sideband that's at lower frequency, one that's at higher frequency. And they come to the beam splitter. Okay? Now let's see what happens to the light that, well, okay. Yeah, maybe I'll just stick with it. Stick with this one. Let's finish with this side. You're coming in, this triad of three electric fields comes and hits the mirror and is transmitted in part. We'll get to what happens over here in a second, and is reflected in part. And what's reflected is, as we'll see in a minute, because there are sidebands on this side too, is only the carrier. Here comes this thing. Well, maybe I should have started. Maybe I should have done it the way I was going to. I'm sorry. Let me start all over. Let me start from the laser. This is the thing. Hits this. It's reflected to this. Let's not worry about that. It's also transmitted. So here it's transmitted. And here is the transmitted peak. That hits this mirror. But remember, this mirror is moving in opposite phase to that mirror. Remember, when this side stretches, this one falls in. When that one stretches, this guy falls in. So the reflection of the sidebands have opposite sign. And so here they are. And you'll notice that the sideband, the high frequency sideband here is negative, whereas it's positive from this mirror. That's that. See, I guess I should have started that way. And then the low frequency sideband is negative here, but reflected from here, it's positive. That's due, the difference in sign between this picture and that picture is due to the gravitational wave. The difference between the two vectors has to do with phase modulation. Okay, now we come to the critical statement which I'm aiming for, which is it comes to this mirror, and this one has a minus sign. What does that mean? It says that the reflected electric field get flipped by 180 degrees. In other words, on this side, when the reflection came on this side of the beam splitter, it did not get, it gets reflected, but didn't get flipped in sign. On this side, it gets flipped in sign. So consequently, when you now take the beam from here and reflect it back this way, okay, you find out that the beam gets inverted. The carrier gets turned upside down, so no carrier goes here. Carrier cancels. And the sidebands add. That's the joy of this. So in other words, when there's no light going to the photodetector, you didn't see any light, but what is going to the photodetector, if there's any motion in these mirrors, the motion of those mirrors does get back to this photodetector. So these sidebands get increased. So what happens, while the same thing happens here, going back to the laser, is that all the light, all the carrier here gets added. Because watch, there's no inversion. When you hit, still no inversion of the carrier, still no inversion coming back. But here what happens is you go in, there's a reflection, and then there is an inversion. There's an inversion to the sidebands, but a sum in transmission. There is no change of sign of the carrier. So all the carrier, but no sidebands go back to the laser. So now you have a complete description of what goes on in a Michelson interferometer in the way you have to understand it for understanding the gravitational wave detectors. Let me say it now slowly. In a Michelson interferometer, if you make this the dark fringe, that means that there is no light going here. That means that the carrier is all going back to the laser. And the sidebands generated by the motion of the gravitational wave on these two things have opposite phase, 180 degrees out of phase. Their sidebands add as they go back to the photodetector, but they do not go to the laser. And that is a critical thing in the whole design of these detectors. Okay. Some people like to think of it that at the detector, and this is very important, you're taking the difference in the phase between the motion of the light, of the whole light, between at the anti-symmetric port it's the phase of one side against the phase of the other subtracted, whereas the sum of the phases is what comes back to the laser. And that's used extensively in trying to make the interferometer. So here then is the whole interferometer. And remember, we had to get a factor of 10 to the 12. And now you have something new has been added to all of this, which is that now let's go back to the familiar part. The familiar part's the laser, the beam splitter, the test mass, and the photodetector. There's some new mirrors in here. The new mirrors are that there are two in one arm, and exactly the same thing in here, and they form something called a Fabry-Perot cavity. As we will see presently, what they do is they cause the light. These are not complete mirrors. This is very much a complete mirror, but this is a slightly transmitting mirror. So is that one. And the light goes through the mirror a little bit, bounces back and forth 300 times, and then comes out again. Same thing happens on this side. So you multiply the time that the gravitational wave is interacting with the light by about 300. It's effectively making the system 300 times longer. That's one way of saying it. I prefer to think of it as time. These then do the trick I just told you. The side bands of the motion build up and they head to the photodetector, but all the light, the carrier light, heads back to the laser. But it doesn't in the real interferometer. In the real interferometer, there's another mirror right here, a partial mirror. And what does that do? Well, it takes the light that is heading back and transmits part of it to the laser. But at the same time, the laser now is a little bit reflected by that. So the laser light itself hits this mirror, a little bit of it's reflected, and that reflected light from the laser and the transmitted light that comes through this from the interferometer are made to interferometrically cancel each other. That means you pick the position of that mirror right, and you put the coding on this right. And so let me show you the arithmetic for that. Well, let me come back to that. Here's the arithmetic for that. And this arithmetic I won't do for everything, but here's the way you would do the arithmetic. You do it by a scattering process. And this is just so you learn how to do this. Here is the electric field. This is this mirror that we call the power recycling mirror. It's that mirror which was between the laser and the beam splitter. And so now here's the light coming in from the laser, and here's the light coming off that mirror. But that has light that's coming in from the interferometer over here. Part of it's reflected, and you add that, as you'll see in the algebra, to the light that goes back into the interferometer, and part of it is transmitted. And this is E-reflected. That's the reflected light to the laser. And what we're going to endeavor to do is show by picking the coefficients of the reflection coefficients and the position of that mirror such that there is no reflected light back to the laser. And what you have to do is you say, look, the way this works is here is the reflected light from the interferometer, which is this stuff right there, coming back from the interferometer. It's the light that left here goes into the interferometer, comes back. It's not completely equal to this because there's a little bit of loss. That's 1 minus A. A is the loss in the interferometer. It's a little smaller. And what you do is you have a transmission of the light by the coding that's on this side. So now you take E source, okay, and you add it. When you want to now calculate what is the E in, you take the electric field multiplied by the transmission, which is the square root of the power transmission. This is the field transmission. And you add it to the field that's been reflected here. That goes like that. So that's the sum. So we now know what the field is that would be heading back. And now the idea is to make this field go to 0. Well, to make that go to 0, you do the following. You take the light from the source, that's from the laser, take that reflected light, which is this one, add it to the light that reflected IFO minus wait a minute. Oh, yeah. I'm sorry. I got myself confused. This is, yeah, no, that's right. This is the light. I'm sorry. This light right here. I'm sorry. I said that wrong to begin with. You want to make the reflected, E reflected 0. So what is E reflected made up of? It's made of this light coming back from the interferometer being transmitted by the by this mirror. So that's this term. And you want to make that get canceled by the term that is the one from the source that gets reflected. So you cancel these two things. When you solve that equation, you find out that you want to make that you solve for what should be the transmission of this mirror, and you find out it just should be equal to the losses in the interferometer. And that allows you, for example, to do something quite fancy. What that does is it makes it so that no light gets reflected here, and the light in here gets increased enormously by a factor of maybe 500. And in the arms, in the interferometers and the interferometer, because that gets reflected over and over again, this might be another factor of 300, 400. So you wind up with maybe 20 watts from here, 800 watts or so from here, and something of the order of hundreds of kilowatts in here. And that's how you ultimately build up the power in the interferometer to get to the point where you can beat that factor of 10 to the 12. It's not only done that way, but that's a good part of it. And the last mirror that I want to talk about is something called the signal recycling mirror, which takes those sidebands, which are the things that come back to the photodetector, and reflects them back into the interferometer for another amplification if they interact with the light. We'll not talk that much about that. You can ask me a question about that mirror, but it is a part of the initial detector. So, oh dear. So let me go forward. What this is a picture that just shows you the sensitivity of a detector that is made like what we're talking about here for position. Imagine the two arms are one arm is here and the other arm is there, and at 45 degrees to that, the interferometer is not sensitive in the plane of the detector, and is sensitive in the for gravitational waves coming from above. And this is for both polarizations. Okay. So anyway, let me now take you to how a Fabry Pro works, and I don't know if I want to do any more than just to show you the relations and show you some pictures of that. But it's the same idea. And if you want to do this for yourself, this is not a bad way to operate, using these scattering matrix ways of doing it. This would be the input mirror for the cavity. That would be the output mirror. That's the place where the light comes in. We usually make the mirror, that output mirror, that's the far mirror away from the beam split, the furthest away, pretty much a pure reflector. And you carry out the same kind of calculation of reflections and transmissions, and you find out a very interesting thing. As you do this, a little feedback equation occurs. This is the algebra for it. You can look at this later in your notes. This is, of course, you'll have this. And you get the transmitted light that goes this way, proportional to the transmission of this mirror, the amplitude of the transmission. We make that very, very small. So most of the light doesn't go, it gets transmitted. But here's the reflected light from a Fabry Pro like this. What it does is it reflects. This is very close to unity, the reflection amplitude, and it's not exactly unity, but close to unity. This is 1. And so this numerator is close to 2 if you make the time it takes the light to go back and forth some multiple of the period of the light. That's what this is. So that's called the resonance condition. And you can make e to the I 2kl. K is the 1 over the wavelength of light with the 2 pi, and L is the length between these two things. Yeah, when this becomes 1, you have a resonance condition, and here the bottom blows up on you. You can see the bottom blows up, and you get the very interesting sort of thing: a 0 divided by a 0, which or something divided by 0. It looks that way. It doesn't behave that way. And let me show you what that looks like. I'll come back to that. So here is what the reflection spectrum of a Fabry-Perot looks like. This is light coming in from the laser, from the beam splitter. And you'll notice two things. This is the red is the amplitude. If it's if all the mirrors are very loss-free, the reflection of a Fabry-Perot detector, a Fabry-Perot cavity is the same, virtually independent of frequency. That's because of that division by almost zero. But the phase of the light that gets reflected changes dramatically in a very, very narrow little band. And that is what is so important in being able to use this in an interferometer. Because if you change the phase, you can get the light to go from dark to bright, or the sidebands to change their sign. So this is the major property of a Fabry-Perot cavity. It's one that reflects. If there are very small losses in the cavity, it reflects the light completely, and it changes the phase over a very small wavelength or very, very small frequency band by 360 degrees. Well, 180 plus 180. Okay, so the other parameter, and this is something, one way of thinking about the cavity, is that if you want to look at the transmitted light, it's something like this. And this is another way of representing it. This is more time-honored. People know more about Fabry-Perots that do this. And here again is the transmission response now of the Fabry-Perot, and it has a peak in the transmission. But you notice it doesn't transmit all the frequencies. It's very narrow. For example, this particular one, which happens to be one of the ones used in the 4-kilometer system in the Ligo, has only a bandwidth of about, maybe 200 hertz on one side. And then it doesn't transmit hardly at all. But the phase shift, even of the transmission, is quite radical. So it's an interesting filter. And here's what that filter looks like. This is something you need to know if you want to understand the sensitivity of the instrument. The Fabry-Perot, as a device to detect the gravitational waves, it generates these sidebands, which come back. We'll talk about that in a minute. And those sidebands have an amplitude which stays pretty constant until you get, for the particular example we have, till you get to about 100 hertz. And then the amplitude of the sidebands slowly disappears, goes towards zero. And the reason why that happens is because the sidebands are moving further and further away from the resonance condition that e to the 2ikl, e to the power 2ikl is going, is 1. And it's beginning to have bigger numbers and different numbers. It's no longer resonant. And the phase changes quite dramatically. I mean, for the sidebands that get generated. So one last thing about the Fabry-Perot, and for those of you who care, here's how the Fabry-Perot works as the detector. And the thing you have to remember is that from the first time, there's no reason you should remember it, but this resonant denominator, right? Sorry, let me get that. Yeah, here we go. This reflected beam from the Fabry-Perot with this term in the numerator, but the important one is the one in the denominator. If e to the I2KL is 1, this is going to be very close to 0 because R1 and R2 are close to 1. 1 is exactly 1, and 1 is a tiny bit smaller than 1. This is called the amplification or the build-up term of the Fabry-Perot. But it gets closer and closer to being a finite number as I to the 2KL goes away from being 1, this number being 1. And so as you build up sidebands in here and here, the sidebands no longer become resonant in the cavity. And so that's what's going to happen here. You'll see that. So here's the idea of the way it works as making sidebands. Here we're interested in, here's again the Fabry-Perot cavity. And here is the input light to the Fabry-Perot cavity. But now there is many more fields in the output light than there were in the input light. If this light is only a carrier, And this mirror has been made to wiggle because of the gravitational wave. That's the key new idea. In other words, this mirror, they both wiggle, but this one is further away from you and the other parts. So this is the one that's doing most of the wiggling due to the excitation by the gravitational wave. Then this mirror does exactly what that mirror does that I showed you, that is making sidebands. So this injects sidebands right here at that point in the scattering equation. That's proportional to the amplitude of E2, the magnitude of the field in E2. That's been built up by the carrier field. E2 is quite large. In fact, it becomes E3 after it's reflected once. Let's do it here. So E3 is quite big. In fact, here you can see what E3 is. It's the input field. Here's something that's close to 1, but divided by its resonance. So this is divided maybe 200-300 times bigger than the input field. So now here come these gravitational wave sidebands. They're generated right here as a derivative of that mirror wiggling with that field on it, the E3 on it. Okay, and so now that begins to rattle back and forth in here. You can just calculate that out and carry it back and forth and back and forth. And as you do that, you'll see this is what you get. You get another multiplication, which is this one. You get a reflected sideband here that now has got a new frequency. It's at the frequency of the positive sideband of the gravitational wave, and it's amplified by this factor. But that factor eventually will move away from the resonance. That's the amplification factor for the carrier. That's the amplification factor for the sideband. And the same thing happens for the other negative sideband. So that's the basis of the way the Fabry-Perot cavity works in the interferometer. It makes these sidebands. And so now you have, for an input carrier, you have 3 waves coming off the input, going back into the instrument from the cavity. One of them is the reflected wave, which is, it's down here. That reflected wave is just the input wave. If you remember right from that first picture I showed you, all the waves reflected from it have the same amplitude. Okay, but these are not reflected waves, these 2 sidebands. These are generated inside the Fabry-Perot cavity, and they make it out, having to be transmitted here. And so consequently, these are the things that there are now 3 waves in the reflected, the carrier and the 2 sidebands. Okay. Whew. And if you want to look at this picture, it's the same picture as we did with the Michelson. I'm not going to walk you through it, but it just shows you that the electric fields generated in the cavities, the sideband fields, get increased, they get made there, and then they get propagated into the interferometer itself, which is here's the Michelson itself. All right, so we're almost there. Before we go on any further, I'd like to stop right here. And are you totally confused? I know I've spent an awful long time now on the instrument, but let me stop. Are there some questions about this?
So please raise your hand if you want to make questions to Professor Weiss, and I or Mikko will open your microphone. And
yeah, I'm going to take 2 or 3. Take 2 or 3 here, not a lot, but aim the questions at something that you didn't understand. Yeah.
I don't see any question.
You don't? So everybody's asleep. Good. Okay. All right.
No, all is very clear.
Oh, yeah. I can't believe that. Okay, let's go on. All right. Well, then, anyway, since I'm taking you through the interferometer, and this is now even a more faithful schematic of the interferometer, and probably the last slide on any of the instrument. But you can see even more complicated things. Here, let me point out the things you know about. Here's the laser. There is the power recycling mirror. Here is the beam splitter. And here's the Fabry-Perot cavity, and another Fabry-Perot cavity. And finally, Here's the photodetector. So what's all this other junk? Well, all this other junk is other cavities that are used to stabilize the frequency of the laser. That's a cavity used to stabilize the frequency of the laser and also to stabilize the light as it goes into the system. This set of mirrors, including the power recycle, these mirrors, these three, are things that convert the laser beam, which might be a millimeter in diameter, to being 6 centimeters in diameter. Oh, 6 centimeters in radius, excuse me, a millimeter in radius, no, probably half a millimeter in radius to 6 centimeters in radius. That's called a telescope. And the beam is very big. It's like the size of your hand. And then there's some extra stuff in here. These are plates that are compensating plates to make the cavity itself, the Michelson cavity, not degenerate, for those of you who know more than most. And then there is now a output. Here's that signal recycling mirror, which sends back that they're all part of the same thing. It's a little telescope on this thing, but here's a signal recycling mirror. It sends all the light back, not the light back, but the sidebands back into the cavity. And here then finally there is something called an output mode cleaner, which cleans up all the errors that might be in the light that comes from all these other mirrors having small errors, so that there's a pure Gaussian beam hitting the photodetector. And then there is, okay, and that makes the contrast of the system. So there's much more, and even still more, and I'm not going to show you more. There's a whole system to keep this aligned. It's a nightmare. That's what I want to tell you. And you need, that thing has servo systems, 10,000 servo systems in it. It's a wonderful instrument, but hard to make go. So now let me quickly talk to you a little bit about noise, but this is going to be done better and differently by via Chatnin. I'm probably, a lot of my lectures now, I don't want to spend, I have a lot of slides I have on this, which I'm going to jump over because I'm now going to rely on Vitachin to do it better. But you ought to know this much. This is the noise plot for the very first detector we built, the 4-kilometer detector. It's not the one that made the detection. We'll get to that one in a second. But this has the clearest noise spectrum. What's being displayed here is not H, but the spectrum of H. How much of each component of H is at each frequency. And you can see here's 100 hertz. And if you want to sort of interpret this, let's take, here is the spectrum of the envelope of the first spectrum of the first detector. It's everything in where it says LIGO 1. And let's take this point right here. Let's make it this point. At 100 hertz, it's about 10 to the minus 23 strain per root hertz. So the way you would interpret that in terms of what Kip told us we needed, that is 10 to the minus 23 times the square root of 100, about 10 to the minus 22 RMS strain at around 100 hertz. It certainly was better than what Kip said, but not very much better. 10 times better than what Kip said. Okay? And here is the envelope of the things that kept it from getting better. The very first thing is the noise, that's the quantum noise of the light. And it has two pieces. It's very much like the Heisenberg microscope. And when you get the notes to this lecture, since you have them all, you'll see a very elaborate presentation about this. But let me just say what happens. It's with the Heisenberg microscope in ordinary quantum mechanics, what you always get this nice conundrum that Heisenberg had. How do you determine the position of an electron with light? Well, if you want to determine it, you hit the electron with light, but that position that you do is limited by how big the wavelength is of the light. And so if you want to improve it, the position measurement, to see the scattering from a smaller region where the electron is, you have to make the wavelength smaller. But if you make the wavelength smaller, you have a larger momentum in the light. Remember, the momentum in the light is equal to the energy in the light divided by the velocity of light. And so it turns out that this is exactly the same thing that happens in these instruments. We're not dealing with one photon. We were dealing with huge numbers, 10 to the 22 per second, something like that. But nevertheless, if you want to improve your ability to determine the position at high frequencies, you want to drive this down. Oops, sorry. you want to drive the shot noise down. It's called, I prefer to call it the phase noise, but everybody calls it the shot noise. It's the phase noise, the intrinsic phase noise in the light. And then you will, to increase that, you have to increase the power. That brings this down, but makes this piece of the curve, which is the radiation pressure noise, get bigger and bigger. Now you notice in the initial detector, we were not limited by that. So that wasn't important to us, but you'll see it becomes more and more important as we get better and better. So that's the quantum noise. And we will see something which I'm not going to leave out, is the wonderful way you look at quantum noise in these detectors. It comes in as from the vacuum fluctuations. We will talk about that. The other noise is thermal noise. The fact that everything is at room temperature, everything is wiggling, and here it's the wiggling of the suspensions of the mirror. And then the seismic noise, which you haven't been able to kill. That's that big factor. How much is the ground shaking? And you do very well as you can, but you can't do well enough. We certainly didn't do well enough in the initial detector. And those three noises, there is much more in this talk about them, but I may not be able to get to them all. And you're going to get a very full talk from, I think it's the second to last talk in the series about the quantum noise and the thermal noise. I'm going to give you a little more about the quantum noise. And so what are the other noises that become, here's the reason you can't have any gas in the tubes. So you have to evacuate the tubes. And at the time when we started, that was plenty good enough. It's no longer. We definitely, and we are at this level, by the way, down here, 10 to minus 9 torr in those tubes. So is Virgo slowly now. Notice they had to get down to here. And so then the one other noise I want to say something to you about, which is the reason why there's a limit to this technique on the ground, and people are thinking of doing it in space. In fact, there's a real program being considered to do this in space, is the gravity gradients. What's that? Those are due to the fact that there are fluctuating normal gravitational fields of a Newtonian variety all around. The atmosphere, its density is changing in frequencies that are important to us, all around the test masses. The ground, due to the fact that there's seismic waves running in the ground, the ground is not only shaking, making accelerations, which you can do something about, but it's also making forces that vary as straight old Newtonian forces on the test masses. And they are getting worse and worse and worse as you get lower and lower in frequency. And so that kills every kind of low frequency measurement on the ground. Now, there are people trying to do things about measuring that. It's hard work. So there is very good reason to go into space if you're interested in looking at gravitational waves, much smaller in frequency than a hertz. At any rate, I don't want to go through all of this. Is a lot of stuff on thermal noise. I just want to go to this one, which is the interferometer. And I do want to, because this is such a charming thing we all had so wrong. If you look at the original papers, this is something that was finally resolved by a very smart graduate student and now a full-time professor, Carlton Caves. He had this right. But where does the quantum noise actually come into the interferometer? And the interesting thing is, I want to spend a few seconds on this, is that here's a Michelson, just like the Michelsons we've been talking about. And it turns out that what comes in with the light is the coherent light, but then there is a fuzzball, the vacuum fluctuations in the radiation field itself, the natural fluctuations, which is that half quantum per mode in the radiation field, puts a fuzzball of either phase or amplitude noise, depending on whether at the instant the vacuum fields are along the direction of the field or perpendicular to it. That's phase noise, but amplitude noise. And they travel, they come from everywhere, and they come in, for example, wherever there's a port into the interferometer. So it turns out the ones that come in with the laser do not bother you. And there's a reason for that. And you can follow this. What they do is make two things. They make phase noise and they make momentum noise, both, just like in the Heisenberg microscope. And what happens is, you can see this here. Let's look at the arrow on this one. This happens to be the direction in which the quantum noise is pointing at this moment. Now look, now you come in with this whole business with what's plus and minus. and you look at what's pushing on the mirror here, this will be whatever field is pushing on the mirror is that carrier plus that green little bit of vacuum fluctuation. You add them. That's done up here in terms of calculating the radiation pressure force on this mirror. Same thing happens here. On this, and here it is coming in here, and same thing happens. The green arrow is not well visible. Nothing has happened to that field. And so that adds in, if the force of the radiation pressure fluctuations adds, and you'll notice something interesting in a minute. Just remember that it's the same sign. It's the green arrow points up, it points up. So when you look at the total force, the radiation pressure force, the fluctuating force, the incoherent force, incoherent field that comes in with the laser field from the symmetric port has a plus sign. Here it also has a plus sign. So it turns out it makes, when it's multiplied by the square to make it into a power, this term and the coherent term multiply together, they push the mass out. The same thing here, pushes the mass out. Well, we're not sensitive to the mass doing the same thing in both. Remember, the place that's sensitive to phase difference or difference in the position is the anti-symmetric port. On the other hand, all those fluctuations will go right back to the coherent place, go back to where the laser light is. So we don't see the noise that comes in with the laser. And that's also true of laser noise. That is the same so it turns out you're very insensitive in this system to noise that fluctuates the endpoint of that electric field of the carrier. That's very different for the situation coming in the anti-symmetric port. Here, because of that minus sign, all hell breaks loose. The fluctuating fields come in, and now you want to follow the blue arrow. Okay, you come in, nothing happens in transmission, but then it gets reflected from with the minus sign. And there becomes a minus sign here that points the opposite way. So now you have a term that multiplies the coherent term, which is the big one. These are tiny terms. I'll give you a feel for these. These are both about 10 in LIGO, about 10 microvolts per meter. If they were, that's the square root of E squared fluctuation. That's 10 microvolts per meter. It's pretty big. And that field is thousands of volts per meter. So it's the product of this term and the coherent term, that's the laser term, that makes the noise. And in this case, the minus sign here and the plus sign there make these, one get pushed in, the other get pulled out. That, in other words, they make them go in opposite directions. That's exactly what we're sensitive to. And so the net noise we see is the fluctuation momentum noise that comes from the input that comes from the anti-symmetric port, not from the symmetric port. So all the noise in the system comes from the anti-symmetric port. That's also true of the phase fluctuations of the light, the intrinsic phase fluctuations of the light. They don't cancel they cancel as you go this way. Though they don't matter as you go that way, but they don't cancel as they come out. The interferometer looks like a mirror to them. So both the phase noise, which is called the shot noise by some people, and the radiation pressure noise comes in from the same port. And I think the man's name I have trouble, Yevachnin, will do a better job of explaining that to you. But I do want to show you a plot which is useful for this, and that is this. This is the noise, just the quantum noise, as in terms of the strain noise that it makes. And this is frequency. And here is the situation for different amounts of power that are in the long arm cavities. And right now we're operating at 100 kilowatts about, we will soon be operating at about 300 kilowatts, we hope, in the arms. We were operating at 100 kilowatts when we made the discovery. And that shows you that, well, you have the momentum noise is this part, and the phase noise is this part. And so we're still in a regime, it turned out, where the phase noise is dominating. And soon, as we increase the power, this begins to get bigger and bigger, and it becomes real part of the noise budget and very serious. So let me not go any further. Let me show you what was done for advanced LIGO. For advanced LIGO, we changed two very important things in the instrument. One of them was we got the thermal noise smaller by using materials in the pendulum. I haven't described that to you, but I think Vaitachin will help you with that. Or you can ask me as a question. I'll show you those slides, but I don't want to take the time now. And what was done is that here are the first line of defense against thermal noise was to build a system with 4 pendula in series. So here's some springs, and imagine this spring is attached to the ground somehow. And here's the first pendulum. And then that pendulum hangs another pendulum. And then from that hangs another one, which is a big piece of glass. And finally, this very precious mirror hangs from the very last one. And so you have 4 stages of isolation of ground noise, seismic noise, each one with a 1 over frequency squared attenuation. And then you have things that don't make thermal noise. The pendulum does not make thermal noise on its own. The gas is small enough so it doesn't push the mirrors around that's in the chambers. That does not do it. It turns out the slight bending that goes on at the base of these fibers is how the thermal noise gets into the system. You bend the fiber a little bit as this oscillates back and forth, and that has energy, but that energy isn't all replaced when you go through one cycle. There's losses in that motion, and wherever there are losses in a mechanical system, that is the place where the thermal noise gets into the system. And you will get a whole theory for that from Vaitachin. Okay, it's called the fluctuation dissipation theorem. It's a very important theorem for our whole field. And now, this thing which has lowered the thermal noise and improved the seismic isolation is hung from a thing which is quite complicated looking, but a very nice idea. What this idea is that we use a whole set of active vibration isolation systems, things with seismometers in them, platforms, one platform after the other. There's an outer platform, a inner platform, and another platform supported by the inner platform. So there's 3 active supports going on here. And the way they work, I'll take one of them. You have a seismometer in one of the supports, inside one of the platforms, and you measure the seismometer output as a function of frequency, and then you push the seismometer with pushers, little electromagnetic pushers, so to cancel the signal in the seismometer. In other words, it's an active way of getting rid of the ground noise, a very successful way. And it's the same kind of thing that happens to you when you many people ride in airplanes, and they get headphones that allows them to listen to music without hearing the noise in the airplane. Those are called active hearing devices. And what it is you have a little microphone that listens to the airplane noise while you're listening to your music. That microphone takes its signal and puts it on top of the music in such a way that it's inverted so that you cancel the contribution of the airplane noise that is inside your headphones. And that's the same idea here. And that can be improved and improved, because the beautiful thing about ground noise that's very different than gravity gradient noise is that we have an inertial frame. There is a way you can find out if you are moving with respect to the inertial frame. That's what the full meaning of F equals ma is. The thing that everybody learns in high school or already learned, first year physics. The force is equal to the mass times the acceleration. But then this acceleration is with respect to something. It's with respect to all the stars, all the things in the universe that make the frame. And so you can set yourself up if you make a very, very delicate device that does not like to be moved with respect to the frame of the stars. And if it moves, it says, there's a force here. Let's see how big it is. And you can use that to cancel the forces that push you around. So that has changed. the spectrum. And no longer here now is a spectrum that we were seeing before. Now this is the one for the advanced detector. It has a completely different, because of this, a different complexion. The black line is here's 100 hertz again, and the purple line is the quantum noise, which now is completely dominating here. It's beginning to dominate even in the region around the 20, 30 hertz, so it's not quite there. And here is a noise that is the thermal noise of something which we hadn't considered. And I know people in Italy are working on it. People all over the world are working on this, on how to reduce it. It's the noise that comes from the thermal acoustic waves induced thermally in the coating of the mirrors, the coating that we put on the mirrors to make them reflect well. And that turns out it's attached to the light by that. And consequently, it turns out to be a very important noise, and we don't quite know how to get rid of it yet. Here are the other noises, which I won't go into, which don't seem to be yet a serious problem. At the very end of the talk, you will see, and that's coming soon, we'll talk about those noises. So this is all the ground noise isolation from everything. It's quite dramatic. But and this is the vacuum. So here now is a little bit about the observatories. Now you will hear much more about the Italian observatory from Lasordo next talk, and he'll talk to you. I think he's going to talk to you about that, but also probably the administration and organization of it, which is probably an interesting story. So there, in this picture, there are three. Well, here are all the possible gravity wave detectors and being planned in the world. There's one in the Pacific Northwest of the United States and one in Louisiana. Those are the ones that made the first detection. Here's Virgo, which was very important in all the other detections. And then that's in Italy near Pisa. And this is a German detector, which is a research detector. They were hoping, in fact, that group should have been the ones that should have made the discovery. They were in the field and doing beautiful work back in the 80s and the 90s. But then German unification cost them. And also the fact that the leader got too old. That's one of the problems that happens when you have the certain social structures. Anyway, let's not get into that. That now has become a research detector, but they are doing, the people who are running GEO are also the people doing the detector in space. So I hope they get their desserts that way. Here is a detector that has been built. It's not yet working completely correctly, but it has some ambitions. It wants to do it in a mountain. They hope to thereby reduce a little bit of the gravity gradient noise, and they want to operate at cryogenic temperature. So two things that people have been talking about for a long time. They're running, but they're not at sensitivity. And then there's a detector that is being, at the very primitive stages, it's being built, and it's being built in India. It's part of it's the same design as Ligo. Okay, so here's the Italian detector near Pisa. It's beautiful, actually the most beautiful part of all the places where the detectors are made. And then here is the thing in Louisiana, looking down on it. That's the LIGO detector in Louisiana. And here's a little very short section of travel log that's the one in the Pacific Northwest. And what's in those concrete covers is a vacuum evacuated tube to do the laser beams. This is the one in Louisiana. And this is the tube itself, which has a pressure of about 10 to the minus 9 torr in it. Here's a laser table, like many of you have in your own labs, and people working on it. And here is the control room for the Louisiana detector, and people learning how to actually run the detector. And here's sort of the history of what happened at the very first detector. And every new detector has this kind of a history. The history is you have to have patience. This is a patience of 7 years. And this is now displacement sensitivity rather than strain. If you want to get strain, divide it by 4,000. And here is 100 hertz right there. And this is sort of the performance over those years. And you can see it's a huge factor. We got better and better and better and better and better and better and better. And finally, at the end, we wound up in about end of 2006 with this curve. And here is the theoretical curve for the detector based on the kind of modeling you can do for all the different noise sources. So we hadn't quite made it. But from 80 hertz to 70 hertz on, we had made design sensitivity. And two things came out of that. We never saw anything, and I'm very proud of this. It was a clean non-detection. No. There was nothing like that. It was, we saw nothing and we didn't expect anybody else to see anything in that data. And so we say that we did not see gravitational waves at the level, anything in this level. You had to do better than this. So that was one thing. And the fact that we had done pretty well already, and the fact that we were only missing this part, which is a hard part, did give us the courage to go and ask the funding agencies for more money. And they gave us more money, and they gave us those things I showed you a second ago, improving the low frequency performance, improving the thermal noise, which is down in here, and improving the seismic noise. So that's what did it. And that what came of that was this. This was the first detection. And this is a picture of it in terms of strain. 10 to minus units of 10 to minus 21. And this is time. And these are the two pictures, one from Livingston. This is the picture from Hanford. This is the southern one. This is the Pacific Northwest. They look very much the same. This is mostly noise, but out of that noise grows something coherent. And the same thing happens at the other site. And they're displaced by about 7 milliseconds. In other words, it's different in time by 7 milliseconds. And you have to take that into account so that you can put them on top of each other. Here's chunk, but there's still noise, but the signals are more correlated. And here, there's noise again. So, okay. And here's the same thing as represented as a frequency spectrum. Here, instead of amplitude, it's the amount of each frequency in this waveform. And here is that measurement of that amount. It's a frequency it's a frequency histogram in effect. And this is for Hanford again. This is for Pacific Northwest. This is for Louisiana. And here's what this sounds like. I don't know if you heard that, but I hope you did. This is another way to listen to it. So anyway, I will leave this go because I'm going to run out of time. But what was seen this was what was seen. It turns out it was a black hole, and that's something will be explained to you better by several of our people. Let Bernie Schutz will be telling you a lot about what I'm about talking is now about the results. All will be better done by Bernie and by Damour. So this will be very, very short. Because I want to get to what the future looks like for the instruments. But here is what there's a little bit of this you have to know. And here is sort of the very first detection. And the one you just saw the waveforms for, and it solves to being 36 solar masses black hole colliding with a 29 solar mass black hole with about 3 solar masses going off into gravitational waves. For that few fractions of a second, this was the brightest thing in the whole universe in terms of the amount of energy that went by you. I mean, that includes everything going on in the universe. It was enormously bright. And then that has to do with this terrible problem that I showed you in the one of the very first slides, that gravity, and let me say it here because it's kind of fun to think about. If this event had taken place at the distance of the sun, suppose this event that had taken place there, and you would have been scared to death. All of us would have been scared to death. Well, what would we have seen? Maybe. Then the strain that you would have experienced is only 10 to the minus 6. In other words, your body would have changed by 1 micron, maybe, or maybe half a micron, or 2 microns. And that's something you can't. I mean, you might hear it in your ear, but you wouldn't certainly feel it. But what went through you is unbelievable. The power that went through you is 10 to the 25 watts per meter squared. And compare that to what the sun normally does. It's about 1 kilowatt per meter squared. That's 10 to the 22 times more energy than the sun puts out to you every day. It's unbelievable the amount of energy that is. And what does that tell you? It tells you that it's extremely difficult for nature to make a gravitational wave. If space is extremely stiff, how do you make that in the tiny, tiny stretch in space? You have to exert an incredible amount of energy. And that's something people who are trying to make weapons out of gravitational waves don't seem to understand. But they will eventually spend a lot of money and waste it. But let's see. At any rate, here then is the next thing we observed. And we didn't believe it, so that's green, and we didn't give it a symbol. That was on, this first one was September 14th, 2015. The one that we believed was this one. And this is the one that actually made many of us believe the whole thing. It's in the September 26th of that year. We saw this very much longer signal, completely different than the first one, and which had the mass of smaller numbers. People had already seen black holes of this kind of mass. And only one solar mass went into gravitational waves. And then we began to see more. And then very important fact happened. Virgo came on the air. And Virgo, not quite as good as LIGO at that time, but it saw the next event. And this was an event in August of 2017. This is a very important event, because what happened now, you were able to have LIGO signals, add Virgo signals, and now you could do something that you couldn't do before. Here's the sky, a picture of the sky. And if you say, where did LIGO say the signal was coming from? It's from this big banana here. And that's about 1,000 square degrees. But if you add Virgo to this, it's only about 30 square degrees. That's still terrible for an astronomer, but it makes it possible, at least for an astronomer, to go look. And that hit us with a vengeance in this. Here are all the black holes that have now been seen. There's something like 60 of them. But that hit us with a vengeance with this source. And that source is something quite different. Here is the sonogram for that, or the spectrum, the acoustic spectrum for it. It lasts for 10 seconds. And it has, let me play it for you, if you can hear it. I'll shut up for a second.
Ray, unfortunately, we can't hear that.
That's because when I came in the second time. Oh, okay.
People who are interested may find this on the, yeah, that should be in the LIGO website. Probably they will find all the time tracks of these events.
They might. I'm sorry. It worked when we first, never mind. It had to do with me being out and in again. That was the problem. Okay, I'm very sorry. But let's say the important part of this is it lasted for a long time, and it was a real wonderful chirp. And whereas the thing which you didn't hear the first time around sounded like like that, it was very bad compared to this. This was a wonderful tone. It's like running your hand on the piano from the bottom of the piano in a glissando, just right up to the top. And the thing there are two things about this that were absolutely critical. One of them was that it was seen by other people. And what is in these pictures here are pictures of the LIGO picture ends sort of at 400 hertz. If we had more sensitivity at high frequencies, it really should go about to 1 kilohertz. And that's a slight displacement here. And here is the sort of time when LIGO signal ended. And here is where a gamma ray telescope picked it up at between 10 and 50 kilovolts. They saw this little thing. And then the same satellite had another channel between 50 and 300 kilovolts, and they saw this thing, which is quite significant. There was another satellite, which was a different satellite completely, which also saw something. And well, a couple of things, that was critical, that they saw this. And the first thing you notice is that it was later identified that that was a neutron star, as we will talk about, but that it came at a neutron star that was something like 140 million years away from us, light years away from us. So it turned out the gravity wave signal, which is this one, and the magnetic signal, that is that one, were traveling together for 140 million years, and the only difference in time between them is of the order of a second or two. That tells you that the gravitational wave is traveling at the same speed as the light wave to a part in 10 to the 15. So you couldn't ask for a better guess by Einstein than that. And this, by the way, was also seen in an interesting way by Virgo. And this, unfortunately, Virgo didn't see the signal, but I will get to that in a second. It gave information that was absolutely critical to finding it, and by astronomers. And here is the same picture of the sky. And the thing is, here are the bananas that are associated with the LIGO detector, these two. And because Virgo didn't see it, and we knew from the detections that had been made by Virgo, they should have seen it. We knew that it was in one of those spots where the detector doesn't work. That angular distribution that I showed you that looked like an acorn or a peanut. And people said, yeah, it's got to be in there because, God damn it, they should have seen it on Virgo. And sure as hell, that's the, if you say it is in there, then you add the Virgo's non-sighting to this, and it suddenly produces a small enough region in the sky so that the ordinary astronomers with telescopes could see it also. And this is the proof of it. Here is a 10 hours after LIGO and Virgo saw it together. There is the galaxy where this happened. That's the name of the galaxy. It's unimportant. And here are stars that are in our own galaxy, but here is the star that wasn't there before. Here's a picture of that same galaxy taken 20 days before. And you'll see the same stars in our galaxy. They're there. And there's even that one. But this was not there. That thing was not there at all. So that was absolute enough proof for something like every astronomer who had a telescope that could get it in the southern sky went after this source and they started looking at it. I am not going to describe any more than what it is because this is going to be the thing that Bernie Schutz has a lot to do with. And he will describe the science that came out of that joint observation, at least I hope he does, between all the different telescopes on the ground. It was probably one of the most interesting things that happened. The black hole discovery was already extremely interesting, but this was even more interesting because it fit in with the rest of astronomy. It fit in with how this new field of infrared and this new field of gravitational wave astronomy was going to fit into the rest of astronomy. It was going to make a profound difference. And what was discovered was the black hole, two neutron stars coming together, joining together, making a big nuclear soup of neutrons. And that made a very sharp display that all the astronomers saw. And then a little bit, almost immediately thereafter, I mean, it didn't take but probably a few seconds, the black hole formed. And many weeks later, people saw in the radio astronomy, saw a jet coming out of it. The gamma ray burst is what was seen already by the people who were seeing it. Could have well be that the seconds are the things between that being the nuclear fluid and the black hole forming. I don't know that. That may not be right. So a lot of people were able, with infrared astronomy to gamma ray astronomy, radio astronomy, had some very interesting things to say. They found out where all the heavy elements came from. They found out that they could do cosmology with this. It's just wonderful. So I'm going to skip this, and I'm going to skip this. And I want to go to this slide and one more, and that'll be the end. I know I'm running over a little now. This is the future for the ground, at least as far as we know. And man, this is probably the most important slide to some of you because some of you might be thinking of going into this field. What's being planned, at least for the ground, is, and now that you are familiar with these pictures, is these are the spectra associated with the instruments that are ahead of us. Now, the instrument that made the detection, the very first black hole detection, is this one. That's the spectrum of the sensitivity of that curve. What's being built right now, and also that made the neutron star discovery. That and Virgo, which I don't have here, but Virgo has a comparable spectrum. LIGO A+, and Virgo has a program for making a next version also, using new ideas, squeezing, dual mode squeezing, many ideas on improving internal technical things in the detector. I don't want to talk about this. This is sort of a notion which I don't think has got, as people at Caltech are working on this, in particular Rana. It's an idea that may be done. I don't know if it will. It's a improvement that could possibly be done in the smaller detectors, but it has to be proved. This has not yet got enough evidence that this is the right thing to do. But what has a lot of push are two ideas, and one in Europe and one in the United States. And that is to build, in Europe, to build something called the Einstein telescope, which is to build underground to get around the gravity gradient noise, some of it, and also some of the seismic noise, to build a triangle, 10-kilometer triangle underground, and make 3 different interferometers around that triangle. That's one idea. And that has a curve which gets you into some interesting regions, which over here we'll talk about in a minute. Then in the United States is the idea of using something on the surface and making instead of making a, now that we know, we see signals. If we had known this ahead of time, we would have made the interferometer a lot longer than 4 kilometers. In fact, my early thinking about this, I always want to make the thing 10 kilometers, but even that isn't big enough to really capture what we now know. To capture what we now know, because we now have seen gravitational waves, you would want a detector that's about 40 kilometers long, 40. And there are surface sites where you can do that, not in Italy necessarily, they are in Australia, they're in the United States, and that could be part of a network of what's called 3rd generation detectors. And that will be the future, and people are thinking about this for the 2030s, okay? And here is sort of a little view of what that would do. What you're seeing in this picture is a view of redshift. That's the distance. When you use the Hubble law, that's also distance to the source. So the further out is the further distance from the Earth. And here is the distribution of all the black holes, we believe, how they're situated in as a function of distance from the Earth. And here are the different instruments and their capability. For example, here is Virgo and Ligo at the time when, well, now pretty much. And here within the range are a lot of black holes, and we're seeing some. We're seeing sort of a black hole every week now, or did. Here is, and then if you build the Cosmic Explorer or the Einstein telescope, you go out to a region where you're looking at the beginning of cosmology. You're looking at the place where you are beginning to see, you're not too far from the Big Bang itself. I mean, you're very far from the Big Bang, 300,000 years from it, but you're not so far away from where the very first stars are being made. In fact, it's probably you can get into that region and maybe a little earlier for that. And you can find out, for example, if there are primordial black holes. That'd be fascinating. The same thing here is for neutron stars, and here again corresponding. So if you want to look at the entire universe and look at these things with a huge rate, so you can really do a lot of new ideas, a lot of physics, not just astrophysics, you would want to build a big detector like this. So now here's my last slide. Yeah. And by the way, those listening, the people who care about this, I'm now at about the time that's 2 hours from when I was started. But if that's too long, just tell me. I probably have another 5 minutes on this slide. Okay, that's the last slide.
Please go ahead.
Go ahead. Okay,
go ahead.
Thank you.
Go ahead.
Yeah, I will. This is the sort of a modus for what's going on in the field right now in different places and into the future a little bit. So here's frequency of the gravitational waves. Here's where we are 10 to the 4. Well, here's 1 hertz, but all the way out to periods of the order of the age of the universe. And here are the strains associated, the H associated with this. And so all the things you've heard about from my talk so far are out here, and including the CE, that Cosmic Explorer, and the Einstein telescope. That would operate in this band down to the 10 to minus 2025 region. That's probably right. And they are looking at high frequency compact objects. They might be looking at things in the universe, even some possibly phase transitions in the universe. We don't know all the things. We simply just don't know all that's in gravitational wave astronomy. We're just starting the field, and it's just amazing what could be there. Here is what's being done in space and at lower frequencies. This will fly. It's called LISA, the Laser Interferometer Space Antenna. And it was a project that was started about the same time as LIGO in the United States, but it was now taken over by the Germans because the Americans lost courage, and it was a pity they did. They still have a part of it, but they don't run the project. And it's now being well done by the group in Hanover and with a lot of help all over Europe. And this will look at gravitational waves by using a triangle, 10 kilometers, no, not 10, a 5 million kilometers, or maybe 2 million kilometers, I don't know which one of the two, arm length equilateral triangle. And running 3 interferometers in that triangle. And this is in a orbit around the sun at the Lagrange point of the sun and the Earth. And this has been tried. People have made a pathfinder for it, which worked beautifully, and now hopes to fly sometime in the 2030s. They're pushing to try to do it a little earlier than that, but I don't know if that will work. Here's another project which is also going on right now, which is to use the pulsars in our own galaxy as clocks. And if a gravitational wave should come through our galaxy, and we are measuring the pulse rate of the clock, all these pulsars, you have to look at them all, a lot of them in the galaxy, you will find an interesting thing that will happen. A gravitational wave will make all the pulsars that are in the east and the west go a little faster, and the ones in the north and the south go a little slower, and then flip. And that's the effect that they're looking for in the pulsar frequencies. And this last experiment is ongoing now. It's probably the most speculative, but I think to me, one of the most interesting of all of them. And that's trying to use the universe itself as a gravitational wave source. In other words, if inflation, which is a theory of how the universe began, which uses the idea that the universe expanded by factors of 2 every 10 to the minus 30 seconds for a huge range of time, an expansion in the beginning, and that was driven by quantum pressure, and it was driven by effectively quantum gravity in a way, a negative gravity. And it was as fast as people think it might be, because it solves a lot of problems of the universe that we already know, that theory. Things that we have measured in the cosmic background radiation are beautifully explained by the idea of inflation. So it has some credibility, but it's a pretty wild idea that the universe is a quantum system, and that quantum system had a lot of fluctuations in it in the beginning. If that's true, it had a lot of gravitational waves. And those gravitational waves are, we have an idea how big they are. They are not going to be detectable directly by the people on the ground, nor by LISA, unfortunately, if the initial calculations are right. But that's not true that there won't be anything from the universe. There may be phase transitions that happen. That could be detectable both by LISA and ground. But I'm talking about the very earliest inflationary period. If that could be detected by another project if we get there. But let's finish with this. And that is that what they're looking for is they're looking at the cosmic background radiation, the electromagnetic radiation, and looking for ways that the plasma itself, the plasma which generated that radiation as it comes to us, got density fluctuations imparted to it that have the right symmetry for having been assembled by gravitational waves. If that's true, that gravitational waves were responsible for the density fluctuations, or a good part of the density fluctuations of the universe that we now see that generates the cosmic background. If that's true, you will see a particular pattern in the polarization of that radiation. And that's called the B mode pattern. And people all over not all over the world, but people in the South Pole, people in Chile with good telescopes, and in Himalayas are looking for specific patterns of the polarization that would tell you that there are primordial gravitational waves. And they thought they saw them about 5 years ago. They had made a mistake. They thought they mistook cosmic dust or dust in our own galaxy for the effect that they were looking for, but they are still working on this thing. And they hope to have some results, well, ever improving results every year. And that's an interesting experiment to look for. So thank you.
Thank you very much, Ray. You gave us an outstanding actually, what I'm really amazed every time I listen to you speaking about these things is that I mean, there are two things that really I find absolutely wrong. The interest, the physical insight that is your final goal, and I think that this kind of search for understanding, this quest for understanding, the passion that you put into this is a precious thing for all the young people who are listening to you. The second thing that you didn't mention, but I want to mention, is that there is really no single part that you didn't improve from the very initial proposal or the very initial designs, either directly by your own work or by the work of people that have been your students. I'm thinking about the work, for instance, on squeeze states made by Matt and other people, also at MIT, as regards the mirrors. And I mean, you gave the first accurate and meaningful description of all noise sources in the instrument, and this was really the starting point for having something that worked. So your ability of moving from very general principles to a practical instrument is something that really is very few examples in all the history of experiments to my knowledge. So again, it has been really a privilege to listen to your presentation, and I would encourage people to make questions, even naive ones, also because there are no naive questions at all. Each question can
I agree with you. There are no naive questions. I completely agree with you. Yeah.
Yeah.
By the way, thank you, but I'm not. Look, there are a lot. I should have said this right from the start. You embarrassed me somewhat, because there are many people who have given their professional lives to this. Many of who invented. I mean, there are people at Caltech, Kip Thorne, Ron Drever, who was very influential.
Yeah.
But we're not done yet. There was this German group of exquisite experimenters, Schilling, Roland Schilling, and Rüdiger.
Those people,
Schilling.
yeah, sure.
Yeah, and in Scotland, look, everybody, there were people doing this thing. So please, it's very sweet of you to give me some credit, but it's a lot of people who are involved in this, and give them all credit, because it was a work of a pleasure to do for a lot of people for a long time. So anyway, let's go to the questions. I would love to hear what they are.
Yes, we have a question. So,
any questions for Professor Weiss?
Yes. So many thanks for your interesting talk. It was a very beautiful overview on this fascinating topic. And yes, we have a question by Giuseppe Di Vieccio. I don't know if you prefer to ask yourself, or I can read the question.
Well, why don't you do it as you want? I mean, I haven't yet heard the question, so let's see if I can understand. Let me see if I can understand it. That's important. Yeah.
So Giuseppe asks, will we ever be able to measure the gravitational wave stochastic background, even though the quantum rumor is so high?
Oh, okay. Let me see if I understand the question. You would like to understand: is there a chance of seeing a cosmic background, stochastic background of cosmic gravitational waves? Is that the question?
Will we ever be able to measure the gravitational wave stochastic background, even though the quantum rumors is so high?
What's that last word? Too high? What?
High. Well, we have a lot of rumor.
Okay.
A lot of noise.
Let me try to answer it. I think it's just a question. I think it is. We had the same problem in the cosmic background measurements directly. There are a lot of problems in measuring a cosmological background of anything. I'll tell you what the problem is. In this case, sort of three problems. It's probably, as whoever asked the question asked the right question. It's probably, of all the things, the most interesting source that we could look for. I mean, to me, it's the most interesting. I've spent much of my life worrying about the beginning and using in terms of the cosmic background radiation, which is fascinating by itself. And what are the problems? The problems are, first of all, that it is the strength of the gravitational waves. That is, there are several people who have calculated this. The person who has done the most first and probably most closest calculation to showing what might come from inflation is Starobinsky. He's a Russian who has written several papers about this, and almost all the calculations that are made use his model. And his model is that there is a quantum noise that comes from the initial fluctuations that were in the inflation. And these fluctuations actually did all these accelerations as the system expanded. And the magnitude of it is, and I'll give it to you in the following sense, it's probably, at this moment, we are looking, every time we look for gravitational waves, every time we make improvements, there are groups within the scientific collaboration of all these groups that looks for how to find a stochastic background. The way that's done is you look by taking the signal from one detector and multiplying it by the signal in the other detector and looking for the cross correlation between the two as a noise, not as a sine wave, but as a noise. And that overlap exists primarily only at low frequencies. And so what happens is that people do that overlap integral and they just want to see, does it exceed the noise that you get, that you have to deal with, and where are the other noise terms that come in? And there are many of them. One of them is just the noise in the detector itself, but that allegedly is not correlated at the two detectors. Okay, so that's very important. There may be magnetic terms that are correlated. You have to take those out. You measure those separately, from thunderstorms. There is something called Schumann resonances that are in the toroidal cavity of the Earth. You have to take those magnetic sensitivities, if you have them, out. The more important one is the one that bothers every astronomer who does cosmology. You have to take out the foreground objects that are also making gravitational noise. For example, in our case, all those unresolved black holes and unresolved neutron star binaries, and maybe all the sources we haven't even looked at yet, that they have to be taken out in some way. And we don't know enough about those sources yet. That's going to be a real problem. We have to learn about that. What are the foreground sources? So I think that's enough. The two big problems are it's small. And it's so small that even if you do everything you say, LIGO on the ground will not do it. It will not be able to measure the Starobinsky level. It could possibly, and this is also true of LISA, will not measure at lower frequencies that Starobinsky background because it's just too small for them to measure. On the other hand, there are ideas that are not as well accepted that there might be phase transitions in the universe when the universe suddenly went from, let's say, all the forces being equal to suddenly some like gravity falling away, and then the weak interactions falling away. That transition, a phase transition in the universe, didn't necessarily happen uniformly over the whole universe. It may have happened in little bubbles and regions. If that's true, there could very well be gravitational waves from those transitions, those phase transitions, and they could be big enough to be seen by LIGO, by ground-based and LISA. So it's not out of the question. However, before I finish, there is, if you're interested, a thing you can go to on the web where people have thought about this enough because they don't want to give up on it. I think it still would be an absolutely fascinating thing to see the primordial gravitational waves, if they really are there. And the B modes, if the B mode experiments see something, there would be a tremendous pressure to do what I'm about to tell you. And that is, if you look in the literature and look in the web, you will find something called Big Bang Observer. Big Bang Observer. That's a whole mission that was considered by a group of people that did the following, that got to the sensitivity, that got to the primordial background. And by doing the following, by combining the technology of LISA with the technology of what has been done with LIGO, or by LIGO and Virgo. And it turns out that I'll just quickly say it and then I'll get to the next question. The sensitivity, this position sensitivity of LIGO is 10 to the minus 18 meters, as you know, where the position sensitivity of LISA is about 10 to the minus 12. So there's a million, factor of a million, less sensitive in position. But it makes up for its sensitivity by having these 2 to 5 million kilometer long arms. That's how LISA gets its sensitivity. So if you could take the LIGO 10 to the minus 18, 10 to the minus 19 meters sensitivity and put it into space and maintain that with its very long baselines, you would have something that's interesting. And that could do and that's what's called Big Bang Observer. And that's a hard thing to do, okay? But it's not out of the question.
So your opinion is that we will get to that precision, right?
Well, I'm hoping something, not my generation, but maybe even your children, not generation, but your children's generation.
Okay. Well, we have another question by Olga Sazina by YouTube. She asked if the LIGO data, or at least a part of it, are publicly available.
Oh, yeah.
And
no.
in what format? In feeds?
Okay.
Maybe?
Yeah. No, that's very important that you know it is available. And there's a lot of controversy about that within the community. But let me say the LIGO data that is 1 year old all of it is on the web. And if you want to learn how to get at it and how it's formatted and what has been done to the data itself, you have to talk. There's much written about it, but I would recommend you talk to Alan. Oh boy. It's
Alan Wiseman.
No, not Alan Wiseman. He's a guy. It's Alan at Caltech. Alan Weisberg, I think it might
Weinstein.
be. Weinstein. Thank you. Alan Weinstein at Caltech has taken on this really very important role as being ambassador for that data. And you look up the LIGO data on the site. Look up LIGO on the site. You will find instructions how to get to Alan and also how to begin. But it's all on the data. What isn't on the site is the most current data. And there are a couple of reasons for that, but mostly it's prioritized for the people who happen to be in the LIGO collaboration. Now, let me tell you, the future in ground-based, at least, I don't know how LISA is tending to do it, but the third generation gravitational wave detectors are not going to do that. They're not going to prioritize it at all. They're going to have money, hopefully, in the funding that's given to them, so that you can hire people to do the curation of that data, so it can be everybody's data right away.
Okay, so we have another question.
Sure.
How could we build a space-based interferometer? How we can do that?
Well, it's being built. I mean, that's what LISA is doing, and I'll tell you what's different about it than what's being done on the ground. LISA was proposed by a committee in 1975, and the man who took it over from that committee is Peter Bender, who is at the University of Colorado, and he was one of the first to sort of strategize exactly how you would do this. And he came up with the orbit for LISA. And the way LISA works, it's an orbit that doesn't need any very little station keeping. In other words, that triangle is inclined to the orbital plane of the Earth around the sun. It's inclined to that orbit. And if you do the classical mechanics for that orbit, you will find out that it's close to stable for an equilateral triangle with arms of millions of kilometers. Okay, so and you don't have to exert a lot of rocketry. In fact, you don't want to do that, although you would disturb the measurements. So the measurements are made very differently than they are on the ground. In the ground experiments, you actually force every mirror to stand still. You have servos. These are feedback systems that make the whole interferometer, everything in it, for all dimensions, for everything it does, it stands absolutely still, and you measure the control signals. You have to apply to have that condition happen. That's called a servo-controlled experiment, and it's the way you can do very high precision experiments. This is not the way the experiment is done in space. And the experiment in space it's done by looking at the Doppler shift of the lasers between the spacecraft. And what you're counting on is that the Doppler, you have enough optical amplifiers of the laser signals at 1 micron, so that you have enough bandwidth in those so that you can have some amount of velocity for all the spacecraft and still be able to get the signals amplified. In other words, it's done by looking at the beat signal between the laser that you send to the neighboring satellite, and it is sent back as an amplified signal back to you on the first satellite. And that's just done in 3 different interferometers all the way around, and all just along one of the arms, each one a separate arm. And as long as the Doppler shift is smaller than the bandwidth of the amplifiers that you can hear the beat, you can remove from that the relative velocities that are due to the motion from the velocities that are due to the gravitational waves. That's the way that's done. And that has a very much lower sensitivity, as I pointed out earlier, than the ground-based. But they get the gravitational wave makes very large, or relatively large velocities of the spacecraft because of the very large separation of the masses.
Okay, right. So we have another question, but I invite the student to ask.
Sure, by all means. By all means,
yes,
go ahead.
Please, Shahir. Sorry for the pronunciation. Please ask your question. You write on the chat, I know, but maybe it's better if you put your question. No? Okay, so I can read. So how long do we have to wait to understand the underlying physics of gravitational wave sources using the detected gravitational wave itself?
Okay, I understand.
Okay.
I don't think you have to wait very long. It's already going on. And you will hear that from other speakers in this series. The person I think who will tell you that the most is Damour, and maybe even Cornish. For example, what's limiting us right now is the signal to noise. We can tell a lot about we have already measured, for example, we certainly measure the masses of the black holes. We can measure their orbital angular momentum. We have a little harder time measuring their spin angular momentum. We have limits on that, but we will get better limits as we get better signal to noise and more information about the polarization. In other words, if it really is a good detection in both Virgo and LIGO, we should be able to get polarization information. We have not been able to do that with LIGO alone. For complicated reasons I don't want to go into, but that's LIGO system was deliberately made not sensitive to polarization. So the thing that's already been seen, which I'm amazed at, is that we can already see a very interesting effect that happens after the black holes have formed, a new black hole. You can see something called the ringing of the geometry. Not only do you see the waveform, I mean, we see the waveform beautifully. We can, and a lot of the tests we have of the relativity theory does the waveform obey the Einstein equations? And by the way, I failed to mention a very important part of that, namely that people now, and Damour will argue a little bit with you about this or me about this, but I will insert that, yes, you can do a lot of the calculations analytically, and he will show you that. But the real evidence that we have understood the Einstein field equations and that they match the waveforms that we have has come from numerical relativity, doing Damour will have a very sharp thing to tell me about that. Yes, that's true, but it isn't really necessary. You'll see. And but the point is that the fact is we have learned enough of how to handle these the theory in a very strong field that of the black holes, that we can match and compare the waveform generated by the analytic methods or the computer numerical methods against the waveform we measure. And the limits that we have are mostly from the noise in our own waveforms, the noise that we haven't yet gotten out of. So we want better detectors in part to improve that. And right now we have found no discrepancies, by the way, at about what I would call, and here is a place where Damour will tell you, and Cornish will tell you, they're at the level of probably 10%. I think we know Einstein is right. The Einstein equations and what we measure come out to be the same, to easily at the 10% level, to at least 10% level, and with some variables even maybe a little better. But the new thing that has been discovered recently in the data of the black hole collisions is that you can see the metric of the space after the black holes have collided. You can see the ringing, which is something that was first solved many years ago. What's called the perturbation calculation will give you that, give you the ringing of the geometry around the black hole when just after the black hole has been formed. And we now see evidence for that. And we haven't yet seen evidence for Hawking's area theorem, but that will come.
Okay. We have another question by YouTube by Pietro Rescigno from the University of Milan. And he asks if you think it will be possible for gravitational waves interferometry to probe phenomena at quantum gravity scales.
Yeah, that's a hard question. It's a good question, but hard. All these questions are good. I'm probably too old and too limited in my imagination, but my first answer is no. Mostly because we're dealing with huge numbers of gravitons in the signals we're seeing. When you put some numbers to paper, I can't give you the number, but it's enormous number of gravitons associated even with our weak signals. So the granularity that you might expect to find, like you do when you look at light or radio waves, when you get down to very weak signals with very few photons, we have no chance of even getting anywhere near that. On the other hand, can we see something when we look at black holes that have to do with quantum theory? Maybe. And I don't know enough about that, and you should ask that of Damour. I don't know enough about how the theory would tell you much about quantum theory, because we don't get near the actual singularity that's in the black hole. See, the singularity, which is called the event horizon, is a mistaken mathematical, and it's a mathematical mistake. It shouldn't. I mean, it's not mathematically wrong. It's just that people thought that was a real singularity, but it isn't. It turns out that if you pick a coordinate system which has time varying with space together, that has a perfectly wonderful continuity. It becomes singular deep inside the black hole, and I don't know how any of the signals that we see have anything to do with that. So I don't know. Now, if we ever get to being able to do if we ever were able to measure the primordial gravitational waves that come from the inflation, suppose that pans out and we can actually do it and do the Big Bang observer, there's a chance we would learn a great deal about quantum theory of gravity in there, because the fluctuations are fluctuations of quantum gravity. That's a way off prospect, but I don't know any of the sources, except there are people who think there is structure in a black hole. You talk to the experts on that, like Kip. Kip doesn't think so, that the structure, but there are some people who think there's a nice thin skin of some sort of scalar quantity on the inside of a black hole that will show up, or they make reflections in the signals. So far, all the signals we have seen, they're not good enough to really do good tests. 10% tests, no better than 10% tests, have not in any way indicated anything that would look unusual compared to the Einstein classical theory. It's a pity, I don't know. And I know there are a lot of people doing tabletop experiments to look entanglement between gravitational objects like pendula and stuff like that. That's going on right now. Maybe they will see something. It's hard. It's not easy. So I'm not optimistic right now.
Okay. So we have time for a very last question by, well, it is acronym, so I don't know the name of our student, but he asked if your opinion about the identity of high-frequency gravitational wave. He said that it seemed that they identify high-frequency signal, we need greater strain amplitude. Our future ground-based observatories will have sufficient sensitivity to identify this type of signal?
That's a good question. Let me sort of repeat the question. When you say high frequency, I hope he means sort of a kilohertz and higher, or are you talking about megahertz? What frequencies are we talking about? Why don't you ask him?
Giulio, you want to unmute your voice? Okay, he say few kilohertz.
Oh no, that's important. Okay, that's going to be done. I think people are trying very, very hard, and you will hear this more from Bernie Schutz. I hope Bernie will tell you about this. I didn't have time to talk about it. Is that when there's a candidate for multiple kilohertz signals, and all of us who are in this field very much would like to make the detectors get so they're sensitive at kilohertz in the upper kilohertz. And I think there's some prospects that will let us do that. Quantum amplifiers, more squeezing, higher power, all of these things are involved, and making longer detectors for high frequencies. I think 4 kilometers is good enough. You just have to really push on getting the phase noise down, and that people can do that. We were hoping to do that. Now, where is this important? And you probably, the person who's asked probably knows this, that's why he or she asked, and that is that in the neutron star collisions, once the neutron stars have completely annihilated and they're now a nuclear fluid that has left a quark fluid effectively, it turns out that some people have been looking at that as a source of gravitational waves, which might be fascinating. In other words, the densities are 10 to the 15, 10 to the 16 grams per centimeter cubed, a completely new regime. It's not the regime you would find inside of a neutron star, even higher density than a neutron star. And that fluid has normal modes. And the normal modes depend on the equation of state of the nuclear material. In other words, the ratio of the pressure to the energy that's stored in it. And so it turns out that there are many, many models for these quark gluon gases, and nobody knows the right model. And it turns out that would be a very interesting measurement to make, to look for these normal modes, which appear somewhere between 800 hertz to about 3 or 4 kilohertz. I don't know if it's as high as 4 kilohertz, but certainly 3 kilohertz. And then a lot of us have been looking at experiments, and so a lot of people have been looking at how to make an experiment that's specifically sensitive at these very high frequencies and give up on a lot of the problems of the low frequencies. And what that allows you to do is to forget so much about the suspensions and all the things that you are worrying about, the low frequency noise in the detector, and really get the phase noise down. I mean, just unbelievable effort to make the phase noise smaller. And that's how we hope to be able to measure these. And that's something which I think is possible within the next 10 years.
Well, it's important. Okay, so I think we can stop here. Many thanks, Professor, for your time, your lecture, and for accepting our invitation.
Well, thank you very much for having me. And yeah, I hope we got some converts into this field. Let's see what happens. Bye-bye. Thank you.
Thank you so much.
Bye-bye.
Bye-bye. Thank you.
Innocence, I think you are muted. We can
I was just saying that, yeah,
Okay.
I was just saying that I was thanking Ray for his fantastic lecture, and I was reminding our listeners that our next lecture will be the day after tomorrow at what time?
Should be 2 p.m. Italian time.
2 p.m. Italian time. Okay, fantastic. Okay, then I'd like to thank the speaker, our attendees. I think it was really a fantastic ride that was made for us possible by Professor Weiss. And I think that the lessons have been recorded and so will probably become available on the YouTube channel. So for those of you who might be interested in following, for instance, some formal developments of the analysis of the various mirrors that are involved in the present design of the interferometers, it would be good to go back and have another look at the slides just to make all the calculations at a more relaxed pace, in a sense. And okay, fantastic. I think that we had a wonderful lesson, and let's look forward to having maybe a little bit less problems with the internet, but probably, hopefully, this will not be the case for the recording. Maybe that one will be complete. And okay, I don't have any other comment or suggestion.
Okay, so see you to the next lesson.
Okay.
Bye-bye.
Everybody.
Bye-bye. See you.